Chapter 1. Number System. Indian and International System of Numeration. Indian System of Numeration. The numeration system used in India is known as the Indian System of Numeration or the Hindu-Arabic System of Numeration. In this system, a number is split up into groups or periods. Starting from the right, the periods are ones, thousands, lakhs and crores. Given below is the place value chart in the Indian system.
The number shown in the above table is read as 87 crore 65 lakh 24,736.
International System of Numeration. The International System of Numeration is followed in most of the countries of the world. In this system also, a number is split up into groups or periods. Starting from the right, the groups are ones, thousands, millions and billions. Given below is the place value chart in the international system. The number in the above table is read as 32,645,203,124. Note: while writing a numeral, we use commas to separate the periods. Place value and face value. In the Indian or international system of numeration, each digit of a number has a place value and a face value. The place value of a digit depends on its position in the number, whereas the face value does not depend on its position. For example, in 6,847, the face value of 7 is 7. Similarly, the face values of 4, 8 and 6 are 4, 8 and 6 respectively. However, the digit 7 has the place value 7 into 1 equal to 7, since it is at the ones place. The digit 4 has the place value 4 into 10 equal to 40, since it is at the tens place. The digit 8 has the place value 8 into 100 equal to 800, since it is at the hundredths place. The digit 6 has the place value 6 into 1000 equal to 6000, since it is at the thousands place. So we can say place value of a digit equal to face value into position value. Expanded form and short form. Expressing a number as the sum of place values of its digits is called its expanded form. The number itself is said to be in the short form or the standard form. For example, expanded form of 35,79,463 equal to 30 lakh plus 5 lakh plus 70,000 plus 9,000 plus 400 plus 60 plus 3.
Here, number on LHS is in the short form or the standard form and the number on RHS is in the expanded form.
Example 1. Separate the periods of the number 36750782 using commas and write the number name according to the Indian system of numeration. Solution. The separation of periods in the given number according to the Indian system of numeration is as follows. We can write the given number using commas as 3, 67, 50, 782. In words, the above number is written as 3 crore 67 lakh 50,782. Example 2. Insert commas in the number 26357008 to separate the periods and write its name according to the international system of numeration. Solution. The separation of periods in the given number according to the international system of numeration is as follows. We can write the given number using commas as 26,357,008. In words, The above number is written as 26,357,008. Example 3. Determine the difference between the place values of the two 8s in 57, 84, 93, 087. Solution. 8 at the second place from the right is at 10th place. So the place value of 8 in 10th place equal to 8 into 10 equal to 80. The second 8 at the 7th place from the right is at 10 lakhs place. So the place value of the second 8 equal to 8 into 10 lakh equal to 80 lakh. Hence required difference equal to 80 lakh minus 80 equal to 79 lakh 99,920. Example 4. Find the difference between the place value and the face value of the digit 2 in 41 lakh 23,569. Solution. Since 2 is in the 10,000s place, so the place value of 2 is 20,000 and the face value of 2 is 2. Hence, required difference equal to 20,000 minus 2 equal to 19,998. Example 5. Write the following numerals in expanded form. Also write the place value of the digit 3 in each numeral. A. 53,06,825. B. 9,08,30,050. Solution. A. Expanded form of 53,06,825 equal to 50 lakh plus 3 lakh plus 6,000 plus 800 plus 20 plus 5. Place value of 3 equal to 3 lakh. B. Expanded form of 9,08,30,050 equal to 9 crore plus 8 lakh plus 30,000 plus 50. Place value of 3 equal to 30,000. Drag each of the following in numeral form. Successor and predecessor. Successor is the number 1 more than the given number, while predecessor is the number 1 less than the given number. For example, the successor of 2,08,089 is 2,08,090. That is 2,08,089 plus 1 equal to 2,08,090. And the predecessor of 2,08,089 is 2,08,088. That is 2,08,089 minus 1 equal to 2,08,088. Comparison of numbers. Following steps are to be followed while comparing large numbers. Step 1. Check the number of digits in each of the given numbers. If the numbers have unequal digits, then the number with more digits will be greater. For example, 7, 45, 52, 823, 8 digits is greater than 46, 63, 571, 7 digits. Step 2. If the numbers have same number of digits, then compare the digits at the leftmost place in both the numbers. The number with greater digit will be greater. For example, 9, 01, 72, 135 is greater than 8, 92, 54, 321. Step 3. If the leftmost digits are equal, then compare the second digits from the left. If the second digits from the left are unequal, then the number with greater second digit will be greater. And if the second digits from the left are equal, then compare the third digits from the left and so on. For example, 34, 22, 851 is greater than 33, 17, 613. 57, 69, 435 is less than 57, 89, 536. Ordering of numbers. Ascending order. Arranging numbers in ascending order means writing them from the smallest to the greatest. Example 6. Arrange the following numbers in ascending order. 8, 42, 73, 952. 12, 35, 598. 9, 45, 872. 7, 82, 58, 354. 97, 32, 589. 8, 95, 385. Solution. Out of the given numbers, 2 are 8-digit numbers, 2 are 7-digit numbers, and 2 are 6-digit numbers. 6-digit numbers are 9, 45, 872 and 8, 95, 385. Clearly, 8, 95, 385 is less than 9, 45, 872. 7-digit numbers are 12, 35, 598 and 97, 32, 589. Clearly, 12, 35, 598 is less than 97, 32, 589. 8-digit numbers are 8, 42, 73, 952 and 7, 82, 58, 354. Clearly, 7, 82, 58, 354 is less than 8, 42, 73, 952. Hence, the ascending order is 8, 95, 385, which is less than 9, 45, 872, which is less than 12, 35, 598, which is less than 97, 32, 589, which is less than 7, 82, 58, 354, which is less than 8, 42, 73, 952. Descending order. Arranging numbers in descending order means writing them from the greatest to the smallest. Example 7. Arrange the following numbers in descending order. 2, 43, 758, 24, 32, 756, 2, 89, 653, 27, 54, 38, 952, 22, 98, 654, 28, 65, 32, 123. Solution. Out of the given numbers, 2 are 9-digit numbers, 2 are 7-digit numbers, and 2 are 6-digit numbers. 9-digit numbers are 27, 54, 38, 952, and 28, 65, 32, 123. Clearly, 28, 65, 32, 123 is greater than 27, 54, 38, 952. 7-digit numbers are 24, 32, 756 and 22, 98, 654. Clearly, 24, 32, 756 is greater than 22, 98, 654. 6-digit numbers are 2, 43, 758 and 2, 89, 653. Clearly, 2, 89, 653 is greater than 2, 43, 758. Hence, the descending order is 28, 65, 32, 123, which is greater than 27, 54, 38, 952, which is greater than 24, 32, 756, which is greater than 22, 98, 654, which is greater than 2, 89, 653, which is greater than 2, 43, 758. Forming numbers by shifting digits. If we interchange the places of digits of a 2-digit number, say 21, we get the result as 12. And we know that 21 is greater than 12. Similarly, after interchanging the places of digits in 75, we get 57, and we know that 57 is less than 75. In a 2-digit number, we can form only one new number by interchanging the digits. However, the interchanging of digits in a 3-digit number gives us many new numbers. Observe the interchanging of digits in a 3-digit number. Say 689. 698 interchanging the digits at tens and ones places. 986 interchanging the digits at hundreds and ones places. Similarly, we can find 4 more 3-digit numbers by interchanging the digits at other places. Example 8. Write all possible 3-digit numbers using the digits 2, 5 and 8. Solution. Keeping 2 at the ones place, we have 582 and 852. Keeping 5 at the ones place, we have 285 and 825. Keeping 8 at the ones place, we have 258 and 528. So the required numbers are 582, 852, 285, 825, 258 and 528. Put the appropriate symbol or in each of the following boxes. Operations on large numbers. We have to learn add, subtract, multiply and divide large numbers in previous classes. Now, let's recapitulate what we have learnt in previous classes. Addition. Example 12. Add 3013831 and 4580319. Solution. Arrange the given numbers in columns and add. Answer is 7594150. Remember, regroup ones into tens, tens into hundreds, and so on. Subtraction. Example 13. Subtract 2370866 from 4892013. Solution. Arrange the given numbers in columns and subtract. Answer is 2521147. Remember, write the bigger number first. Multiplication. Example 14. Multiply 2851 by 205. Solution. Answer is 584455. Division. Example 15. Divide 625125 by 125. Solution. Hence, 625125 divided by 125 equal to 5001. Use of large numbers in daily life. Example 16. In a state, the number of bicycles sold in a year 2009 to 2010 was 7,43,214. In the year 2010 to 11, the number of bicycles sold was 8,112. In which year were more bicycles sold and by how many? Solution. Clearly, 8,112 is greater than 7,43,214. So, in the year 2010 to 2011, more bicycles were sold. Now, 8,112 minus 7,43,214 equal to 56,898. Hence, in the year 2010 to 2011, 56,898 more bicycles were sold. Example 17. Profit earned by a company in the year 2009 was 6,36,600 rupees. It increased by 89,988 rupees in 2010. What was the total profit earned by the company in 2 years? Solution. Profit earned in 2009 equal to 6,36,600 rupees. Profit earned in 2010 equal to 6,36,600 rupees plus 89,988 rupees equal to 7,26,588 rupees. Now total profit earned by the company in 2 years equal to 6,36,600 rupees plus 7,26,588 rupees. That is 6,36,600 rupees plus 7,26,588 rupees equal to 13,63,188 rupees. Hence, total profit earned by the company in 2 years equal to 13,63,188 rupees. Example 18. The number of sheets of paper available for making notebooks is 75,000. Each sheet makes 8 pages of a notebook. Each notebook contains 200 pages. How many notebooks can be made from the paper available? Solution. It is given that each sheet makes 8 pages. Therefore, 75,000 sheets will make 75,000 into 8 pages. That is, 75,000 into 8 equal to 6 lakh. Thus, 6 lakh pages are available for making notebooks. It is given that 200 pages make one notebook. Therefore, 6 lakh pages will make 6 lakh divided by 200 equal to 3,000 notebooks. Hence, 3,000 notebooks can be made from the given sheets of paper. Example 19. A car covers 1,200 km in 24 hours. Find the distance covered by the car in 1 hour. Solution. Distance covered by the car in 24 hours equal to 1,200 km. Distance covered by the car in 1 hour equal to 1,200 km divided by 24 equal to 50 km. Hence, distance covered by the car in 1 hour equal to 50 km.
Estimation or rounding of numbers or approximation.
Numbers are very commonly used in our day-to-day life. In general, we need to state the exact number as an answer to the question, which requires us to tell about how many. But in some situations, we need only a rough estimate of a number. Instead of telling the exact number, we put forth an approximately estimated number. For example, approximately 6 lakh people travel daily by metro train in Delhi. Mr. Sharma needs approximately 95,000 rupees for household expenses. Let us learn about some methods of estimation. Estimating a number to the nearest 10. To round off a number to the nearest 10, consider ones digit. If ones digit is less than 5, then replace ones digit with 0 and leave the tens digit unchanged. If ones digit is greater than or equal to 5, then replace ones digit with 0 and change the tens digit to the next higher digit. Example 20. Round off 24 to the nearest 10. Solution. Since 4 is less than 5, so 24 will be rounded off to the nearest 10 as 20. Example 21. Round off 37 to the nearest 10. Solution. Since 7 is greater than 5, so 37 will be rounded off to the nearest 10 as 40. Estimating a number to the nearest 100. To round off a number to the nearest 100, consider tens digit. If tens digit is less than 5, then replace ones and tens digits by 0 and leave the hundredths digit unchanged. If tens digit is greater than or equal to 5, then replace tens and ones digits by 0 and change the hundredths digit to the next higher digit. Example 22. Round off 499 to the nearest 100. Solution. Since 90 is greater than 50, so 499 will be rounded off to the nearest 100 as 500. Estimating a number to the nearest 1000. To round off a number to the nearest 1000, consider hundredths digit. If hundredths digit is less than 5, then replace ones, tens, and hundredths digits by 0 and leave the thousands digit unchanged. If hundredths digit is greater than or equal to 5, then replace hundredths, tens, and ones digits by 0 and change the thousands digit to the next higher digit. Example 23. Round off 2314 to the nearest 1000. Solution. Since 300 is less than 500, so 2314 will be rounded off to the nearest 1000 as 2000. Estimating the sum.
Suppose during a visit to a mall, you plan to buy a pullover, a pair of goggles, and a practical notebook. These items cost 675 rupees, 334 rupees, and 90 rupees respectively. To have a quick idea of how much money is needed to buy these items is to round off their prices as 700 rupees, 350 rupees, and 100 rupees.
Adding the rounded off prices 700 rupees plus 350 rupees plus 100 rupees, you get the total as 1150 rupees. So you should have approximately 1150 rupees in your pocket to do the desired shopping. This example suggests that there are no hard and fast rules for estimation. We have to find out a reasonable and meaningful estimate that should be close to the actual answer. Example 24. Estimate 4,560 plus 14,444 to the nearest 1000. Solution. 4,560 can be rounded off as 5,000. 14,444 can be rounded off as 14,000. Therefore, estimated sum equal to 5,000 plus 14,000 equal to 19,000. Remember, the general rule for estimation is round off each number to its greatest place and then add, subtract, or multiply. Estimating the difference. Example 25. Estimate the difference between 6,780 and 925. Solution. 6,780 to 7,000, rounding off to the nearest thousand. 925 to 1,000, rounding off to the nearest thousand. Therefore, estimated difference equal to 7,000 minus 1,000 equal to 6,000. Estimating the product. To estimate the product of two numbers, say 368 and 5,756, round off 368 to the nearest hundred as 400 and 5,765 to the nearest thousand as 6,000. Thus, the product of 400 and 6,000 gives the result as 400 into 6,000 equal to 24 lakh. Example 26. Estimate 183 into 54. Solution: 183 to 200, rounding off to the nearest hundred. 54 to 50, rounding off to the nearest 10. Estimated product equal to 200 into 50 equal to 10,000. Estimating the quotient. To find the estimated quotient of 369 divided by 77, round off 369 to the nearest hundred as 400 and 77 to the nearest tens as 80. So 400 divided by 80 gives a result as 5. Example 27. Estimate 520 divided by 17. Solution: 520 to 500, rounding off to the nearest hundred. 17 to 20, rounding off to the nearest 10. Estimated quotient equal to 500 divided by 20 equal to 25. Roman numerals. There are 7 symbols, numerals in the Roman numerals. These symbols along with the corresponding Hindu-Arabic numerals are given below. Roman numerals, Hindu-Arabic numerals: I 1, V 5, X 10, L 50, C 100, D 500, M 1000. Using these symbols, we can write any Roman numeral by following certain rules. Rule 1. If a symbol is repeated, its value is added as many times as it occurs. For example, double I equal to 1 plus 1 equal to 2. Double X equal to 10 plus 10 equal to 20. Triple I equal to 1 plus 1 plus 1 equal to 3. Triple X equal to 10 plus 10 plus 10 equal to 30. Remember, a symbol is never repeated more than 3 times. The symbols V, L and D are never repeated. Only I, X, C and M are repeated. Rule 2. If a symbol of smaller value is written to the right of a symbol of greater value, we add its value to the value of greater symbol. For example, VI equal to 5 plus 1 equal to 6. VII equal to 5 plus 2 equal to 7. VIII equal to 5 plus 3 equal to 8. XI equal to 10 plus 1 equal to 11. XII equal to 10 plus 2 equal to 12. LXV equal to 50 plus 10 plus 5 equal to 65. Rule 3. If a symbol of smaller value is written to the left of a symbol of greater value, we subtract its value from the value of greater symbol. For example, IV equal to 5 minus 1 equal to 4. IX equal to 10 minus 1 equal to 9. XL equal to 50 minus 10 equal to 40. XC equal to 100 minus 10 equal to 90. Rule 4. The symbols V, L and D are never written to the left of a symbol of greater value. that is V, L and D, are never subtracted. The symbol I can be subtracted from V and X only. The symbol X can be subtracted from L and C only. The symbol C can be subtracted from D and M only. Rule 5. If a smaller numeral is placed between two larger numerals, it is always subtracted from the larger numeral immediately following it. For example, xiv equal to 10 plus 5 minus 1 equal to 14. Xix equal to 10 plus 10 minus 1 equal to 19. Cxiv equal to 100 plus 10 plus 5 minus 1 equal to 114. Rule 6. If a bar is placed over a numeral, it is multiplied by 1000. For example, bar V equal to 5000, bar X equal to 10,000. Learn these Roman numerals: 1 I, 2 double I, 3 triple I, 4 IV, 5 V, 6 VI, 7 V double I, 8 V triple I, 9 IX, 10 X, 11 XI, 12 X double I, 13 X triple I, 14 XIV, 15 XV, 16 XVI, 17 XV double I, 18 XV triple I, 19 XIX, 20 double X, 30 triple X, 40 XL, 50 L, 60 LX, 70 L double X, 80 L triple X, 90 XC, 100 C, 500 D, 1000 M. Example 28. Write each of the following in Roman numerals: A 69, B 89, C 175, D 342, E 614, F 996, G 1679, H 4592, I 16454, J 26495. Solution: A 69 equal to 60 plus 9 equal to 50 plus 10 plus 9 equal to L plus X plus IX equal to LXIX. B 89 equal to 80 plus 9 equal to 50 plus 30 plus 9 equal to L plus triple X plus IX equal to LXXXIX. C 175 equal to 100 plus 50 plus 20 plus 5 equal to C plus L plus double X plus V equal to CLXXV. D 342 equal to 300 plus 40 plus 2 equal to triple C plus XL plus II equal to triple C XL II. E 614 equal to 600 plus 10 plus 4 equal to DC plus X plus IV equal to DCXIV. F 996 equal to 900 plus 90 plus 6 equal to 1000 minus 100 plus 90 plus 6 equal to CM plus XC plus VI equal to CMXCVI. G 1679 equal to 1000 plus 600 plus 70 plus 9 equal to M plus DC plus LXX plus IX equal to MDC LXX IX. H 4592 equal to 4000 plus 500 plus 90 plus 2 equal to bar IV plus D plus XC plus II equal to bar IV dx CII, I 16,454 equal to 16,000 plus 400 plus 50 plus 4 equal to bar XVI plus CD plus L plus IV equal to bar XVI CD LIV. J 26,495 equal to 26,000 plus 400 plus 90 plus 5 equal to bar double XVI plus CD plus XC plus V equal to bar double XVI
CDXCV.
Example 29. Write each of the following in Hindu-Arabic numerals. A. Double XIX. B. Triple CXL. C. CDXLVI. D. CLXV. E. Bar VI CMXXI. F. Bar XLI CCVI. G. MCIX. H. Bar X IDCCC XCII. I DCXCVII. J. Bar LIX CLXIX. Solution. A. Double XIX equal to double X plus IX equal to 20 plus 9 equal to 29. B. Triple CXL equal to triple C plus XL equal to 300 plus 40 equal to 340. C. CDX LVI equal to CD plus XL plus VI equal to 400 plus 40 plus 6 equal to 446. D. CLXV equal to CL plus X plus V equal to 150 plus 10 plus 5 equal to 165. E. Bar VI CM double XI equal to bar VI plus CM plus double X plus I equal to 6,000 plus 900 plus 20 plus 1 equal to 6,921. F. Bar XLI double C VI equal to bar XLI plus double C plus VI equal to 41 into 1,000 plus 200 plus 6 equal to 41,206. G. MCIX equal to MC plus IX equal to 1,100 plus 9 equal to 1,109. H. Bar XI DCCC X CII equal to bar XI plus DCCC plus XC plus II equal to 11,000 plus 800 plus 90 plus 2 equal to 11,892. I DCX CVII equal to DC plus XC plus VII equal to 600 plus 90 plus 7 equal to 697. J. Bar LIX CLXIX equal to bar LIX plus CLX plus IX equal to 59 into 1,000 plus 160 plus 9 equal to 59,169.
Write each of the following in Roman numerals. Write each of the following in Hindu-Arabic numerals. Multiple choice questions, MCQs.
Chapter 2. Whole numbers. Representation of whole numbers on the number line. We can represent whole numbers on a number line in the following ways. Draw a line and mark a point, say O, on extreme left on it. Mark points A, B, C, D, E, etc. to the right of O at equal intervals. Label the point O as 0 and points A, B, C, etc. as 1, 2, 3, etc. Characteristics of a number line. No whole number exists on the left of 0, and every number on its right is greater than it. The number line for whole numbers extends indefinitely on the right of 0. A whole number on the number line is greater than the whole number on its left. Example, 35 is greater than 34. 79 is greater than 78. 278 is greater than 277, and so on. A whole number on the number line is less than the whole number on its right. Example, 10 is less than 11. 148 is less than 149. 440 is less than 441, and so on. A whole number may lie between any two non-consecutive whole numbers. Example, 30 lies between 29 and 31. It also lies between 25 and 32. That is, 29 is less than 30 and 30 is less than 31, and 25 is less than 30, which is less than 32. We can add, subtract, and multiply whole numbers on the number line. Operations on whole numbers on the number line. Addition on the number line. Let us add 4 and 5 on the number line. First, we locate 4 on the number line and then move 5 steps to the right side. We reach 9. Therefore, 4 plus 5 equal to 9. Subtraction on the number line. Let us subtract 3 from 8 on the number line. First, we locate 8 on the number line and move 3 steps towards the left. We reach 5. Therefore, 8 minus 3 equal to 5. Multiplication on the number line. We know that multiplication is repeated addition. Small numbers can be multiplied on a number line. Let us multiply 3 and 4. To find 3 into 4, we start from 0 and move 3 units at a time. Mark 4 such moves to reach the answer. Or, we can also move 4 units at a time and make 3 such moves. So, 4 into 3 equal to 12, or 3 into 4 equal to 12. Fill in the blanks with suitable numbers using the properties of addition and subtraction of whole numbers. Find the missing digit. Complete the following number statement. Patterns in whole numbers. We can find many patterns in numbers. Look at some number patterns shown below. 1 into 8 plus 1 equal to 9. 12 into 8 plus 2 equal to 98. 123 into 8 plus 3 equal to 987. 1234 into 8 plus 4 equal to 9876. 12,345 into 8 plus 5 equal to 98,765. 1 into 9 plus 1 equal to 10. 12 into 9 plus 2 equal to 110. 123 into 9 plus 3 equal to 1110. 1234 into 9 plus 4 equal to 11,110. 12,345 into 9 plus 5 equal to 1,11,110. Let us try to arrange numbers in elementary shapes made up of dots. The shapes we take are a line, a rectangle, a square, a triangle. Every number should be arranged in any one of these shapes. No other shape is allowed. Lines. Every number can be arranged as a line. The number 2 is shown as, the number 3 is shown as, and so on. Remember, 1 is a special number that can be used to represent a line, a square, a triangle, etc. Rectangles. Some numbers can be shown as rectangles. The number 6 can be shown as. In A, there are 2 rows and 3 columns. In B, there are 3 rows and 2 columns. Squares. Some numbers like 4, 9, 16, etc. can be arranged as squares as shown below. Since number 4, 9, 16, etc. represent squares, they are known as square numbers. Triangles. Numbers like 3, 6, 10, etc. can be arranged as triangles, so they are known as triangular numbers. 3, 6, 10. Remember, for triangular number patterns, the number of dots in the rows starting from the bottom row should be like 5, 4, 3, 2, 1. The top row should always have 1 dot. Magic square. Magic square is an arrangement of numbers having the same number of rows and columns. The sum of the numbers in each row, column, or diagonal is the same. The adjacent square is an example of a magic square. Let us check the sum of the numbers in rows, columns, and diagonals in the given magic square. Row 1 equal to 3 plus 2 plus 7 equal to 12. Row 2 equal to 8 plus 4 plus 0 equal to 12. Row 3 equal to 1 plus 6 plus 5 equal to 12. Column 1 equal to 3 plus 8 plus 1 equal to 12. Column 2 equal to 2 plus 4 plus 6 equal to 12. Column 3 equal to 7 plus 0 plus 5 equal to 12. Diagonal 1 equal to 3 plus 4 plus 5 equal to 12. Diagonal 2 equal to 7 plus 4 plus 1 equal to 12. Example 17. Find the values of A, B, and C in the following magic square. Solution. Sum of numbers in column 3 equal to 8 plus 1 plus 6 equal to 15. Now, 4 plus A plus 8 equal to 15. A equal to 15 minus 4 plus 8 equal to 15 minus 12 equal to 3. A equal to 3. 9 plus B plus 1 equal to 15. B equal to 15 minus 9 plus 1 equal to 15 minus 10 equal to 5. B equal to 5. C plus 7 plus 6 equal to 15. C equal to 15 minus 7 plus 6 equal to 15 minus 13 equal to 2. C equal to 2. So, equal to Study the following patterns and find the rule. Then, using the rule, fill in the blanks. Multiple choice questions, MCQs. Chapter 3. Factors and Multiples. Introduction. In lower classes, we have learnt about factors and multiples. In this chapter, we will review these concepts and learn more about them. Let's start recapitulation with the following. What could be the possible ways to arrange 10 objects as a rectangle? There are 4 possible ways to get a rectangular array from 10 objects. Observe the given arrangements. If you multiply the number of rows with the number of circles in each row, the answer is 10. Thus, 10 into 1 equal to 2 into 5 equal to 5 into 2 equal to 1 into 10. In 10 equal to 2 into 5, you can notice that 10 is exactly divisible by both 2 and 5. The numbers 2 and 5 are called the factors of 10. The other factors of 10 are 1 and 10. Factors and multiples. Factors. A factor of a number is an exact divisor of the number. Example, in 35 divided by 7 equal to 5 or 35 divided by 5 equal to 7. 7 is a factor of 35 as it exactly divides 35. Similarly, 5 is also a factor of 35. A given number may have more than 2 factors. Example,
Factors of 12 are 1, 2, 3, 4, 6, 12.
all these numbers divide 12 exactly, so these are all factors of 12. Multiples. A number is said to be a multiple of any of its factors. Example, 12 equal to 1 into 12, 12 equal to 2 into 6, 12 equal to 3 into 4. This shows that 1, 2, 3, 4, 6 and 12 are the factors of 12. In other words, we can say that 12 is the multiple of each of the numbers 1, 2, 3, 4, 6 and 12. Properties of multiples. Every number is the multiple of 1. Example, 64 into 1 equal to 64. 174 into 1 equal to 174. 205 into 1 equal to 205. Every number is the multiple of itself. Every multiple of a number is either greater than or equal to the given number. Example, multiples of 8, 8, 16, 24, 32, 40 and so on. Multiples of 12, 12, 24, 36, 48, 60 and so on. The first and the smallest multiple of every number is the number itself. The multiples of a number are infinite. Example 1. Find all the factors of 32. Solution. 32 equal to 1 into 32 equal to 2 into 16 equal to 4 into 8. Thus all the factors of 32 are 1, 2, 4, 8, 16, 32. Example 2. Is 15 a factor of 17,535? Solution. To find whether 15 is a factor of 17,535 or not, we divide 17,535 by 15 and check if the remainder is 0 or not. Remainder is 0. So 15 is a factor of 17,535. Sieve of Eratosthenes. This method of finding prime numbers was invented by the Greek mathematician Eratosthenes. It is known as sieve of Eratosthenes. Using this method, we can find prime numbers from 1 to 100 in the following ways. List all the numbers from 1 to 100. Cross out 1 because it is not a prime number. Encircle 2 and cross out all the multiples of 2 excluding 2, that is 4, 6, 8, 10, 12 and so on. Encircle 3 and cross out all the multiples of 3 excluding 3, that is 3, 6, 9, 12 and so on. The next uncrossed number is 5. Encircle 5 and cross out all the multiples of 5 excluding 5. Continue this process until all the numbers in the list are either encircled or crossed out. All the encircled numbers are prime numbers and crossed out numbers except 1 are composite numbers. Result: the following results are evident from the sieve of Eratosthenes. 2 is the smallest and only even prime number.
There are 25 prime numbers up to 100.
Properties of prime numbers.
A number with only two factors, 1 and the number itself, is called a prime number.
The smallest and the only even prime number is 2. When two prime numbers are the factors of a number, then their product is also a factor of the number. Example 3 and 5, both are the factors of 75. Now 3 into 5 equal to 15 and 15 is the factor of 75. That is 75 divided by 15 equal to 5. Example 6. Write 7 consecutive composite numbers less than 100 so that there is no prime number between them.
Solution: such numbers are 90, 91, 92, 93, 94, 95 and 96. Example 7. Check the following for prime or composite numbers.
Solution: 13 equal to 1 into 13. It has only two factors, so it is a prime number. 27 equal to 3 into 3 into 3. It has more than two factors, so it is a composite number. Similarly, 29 equal to 1 into 29, prime. 52 equal to 2 into 2 into 13, composite. 53 equal to 1 into 53, prime. 61 equal to 1 into 61, prime. 63 equal to 3 into 3 into 7, composite. 79 equal to 1 into 79, prime. Thus, 13, 29, 53, 61 and 79 are prime numbers, while 27, 52 and 63 are composite numbers. Example 8. Express each of the following as the sum of twin prime numbers. 24, 60. Solution: A. 24 equal to 11 plus 13. B. 60 equal to 29 plus 31. Example 9. Express each of the following as the sum of two odd prime numbers. A. 32. B. 44. Solution: A. 32 equal to 13 plus 19. B. 44 equal to 13 plus 31. Express the following as the sum of two odd primes. Drag each of the following numbers as the sum of twin primes. State true or false. Common factors and common multiples. Common factor. A number that is a factor of two or more numbers is called a common factor of the numbers. For example, factors of 40, 1, 2, 4, 5, 8, 10, 20, 40. Factors of 16, 1, 2, 4, 8, 16. Common factors of 40 and 16, 1, 2, 4, 8. Thus, common factors of 40 and 16 are 1, 2, 4 and 8. Common multiple. A number that is a multiple of two or more numbers is called a common multiple of the numbers. For example, multiples of 3 are 3 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, 36, and so on. Multiples of 6 are 6, 12, 18, 24, 30, 36, 42, and so on. Common multiples of 3 and 6 are 6, 12, 18, 24, 30, 36, and so on. Example 13. Find the common factors of 15, 30, and 75. Solution. Factors of 15 are 1, 3, 5, 15. Factors of 30 are 1, 2, 3, 5, 6, 10, 15, 30. Factors of 75 are 1, 3, 5, 15, 25, 75. Thus, the common factors of 15, 30, and 75 are 1, 3, 5, and 15. Example 14. Find the common multiples of 3 and 4. Solution. Multiples of 3 are 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, 36, and so on. Multiples of 4 are 4, 8, 12, 16, 20, 24, 28, 32, 36, 40, 44, 48, and so on. Common multiples of 3 and 4 are 12, 24, 36, and so on. Prime factorization. The process of expressing a number as a product of its factors is called factorization. Let us factorize 42. 42 equal to 2 into 21 equal to 2 into 7 into 3, or 42 equal to 3 into 14 equal to 3 into 2 into 7, or 42 equal to 6 into 7 equal to 2 into 3 into 7. On observing carefully, we notice that in each factorization of 42, we ultimately get 2 into 3 into 7, which are prime numbers. The process of expressing a number as a product of its prime factors is called prime factorization. Consider the number 36 and its factors. 36 equal to 2 into 18 equal to 2 into 2 into 9 equal to 2 into 2 into 3 into 3, or 36 equal to 3 into 12 equal to 3 into 3 into 4 equal to 3 into 3 into 2 into 2, or 36 equal to 4 into 9 equal to 2 into 2 into 3 into 3. Thus, we conclude that every composite number has only one prime factorization, or every composite number can be factorized into prime factors in only one way. This property is known as unique factorization property. Prime factorization can be done by the following two methods: factor tree method, division method. Factor tree method. We can represent the prime factorization of a number by a factor tree. In this method, in each step, the given composite number is written as the product of its factors until we get all the prime factors. Let us factorize 90 by factor tree method. 90 equal to 3 into 3 into 2 into 5. Let us factorize another number 130 by factor tree method. 130 equal to 2 into 5 into 13. Remember, multiply all the prime factors to get the original number. Division method. In this method, the given number is divided by different prime numbers starting with the smallest prime number. The process continues until the quotient itself becomes a prime number. Let us factorize 630 and 20,570 by division method. A. 630. Start with the smallest prime number. Remember to use only prime numbers. Therefore, 630 equal to 2 into 3 into 3 into 5 into 7. B. 20,570. Therefore, 20,570 equal to 2 into 5 into 11 into 11 into 17. Express each of the following as a product of prime factors. Highest common factor HCF. The highest common factor HCF of two or more numbers is the number which is the greatest common factor to all the given numbers. Consider three numbers 12, 16 and 24. Factors of 12 are 1, 2, 3, 4, 6, 12. Factors of 16 are 1, 2, 4, 8, 16. Factors of 24 are 1, 2, 3, 4, 6, 8, 12, 24. Common factors of 12, 16 and 24 equal to 1, 2, 4. Out of these common factors, 4 is the greatest factor. So the HCF of 12, 16 and 24 is 4. Also observe that 24 is completely divisible by 4. So HCF of given numbers is the greatest number which will divide the given numbers exactly. That is why HCF is also known as the greatest common divisor. HCF can be found by using the following methods: prime factorization method, division by common factors, continued division method. HCF by prime factorization method. Generally, this method is used to find the HCF of small numbers. In this method, following steps are involved: find the prime factors of the given numbers, find the common prime factors, multiply the common prime factors, their product is the HCF of given numbers. Example 15. Find the HCF of 24 and 32 by prime factorization method. Solution. First, find the prime factorization of 24 and 32. Finding common factors of 24 and 32. 24 equal to 2 into 2 into 2 into 3. 32 equal to 2 into 2 into 2 into 2 into 2. So HCF equal to 2 into 2 into 2 equal to 8. HCF using division by common factors. For finding HCF using division by common factors, we follow these steps. Divide the given numbers by a prime factor which is common to all of them. Go on dividing the quotients until they have no common factors. When further division of quotients by a common factor is not possible, stop the division and multiply the common factors used so far. The product is the HCF of the given numbers. Example 17. Find the HCF of 36, 144 and 252 using division by common factors. Solution. We cannot find any common factor further. So HCF equal to product of all common factors equal to 2 into 2 into 3 into 3 equal to 36. HCF by continued division method. For large numbers, continued division method is used to find the HCF. This method involves the following steps. Divide the larger number by the smaller number. If the remainder is 0, then the smaller number is the HCF. If remainder is not 0, then divide the previous divisor by the remainder. Continue the process till the remainder is 0. The last divisor is the required HCF of the given numbers. Example 19. Find the HCF of 783 and 513 by continued division method. Solution. Here 513 is less than 783. So we divide 783 by 513. The last divisor is 27. So the required HCF is 27. Lowest common multiple, LCM. We know that a number which is a multiple of 2 or more numbers is called a common multiple. Let us find the common multiples of 6 and 12. Multiples of 6 are 6, 12, 18, 24, 30, 36, 42, 48, 54, 60 and so on. Multiples of 12 are 12, 24, 36, 48, 60, 72, 84, 96, 108, 120 and so on. The numbers 12, 24, 36, 48 and 60 are the multiples of 6 and 12 both. Hence the common multiples of 6 and 12 are 12, 24, 36, 48, 60 and so on. Let us now understand the concept of the lowest, least common multiple. The lowest common multiples of 2 or more given numbers is also called the least common multiple, LCM of those numbers. In the above example, the least common multiple of 6 and 12 is 12. That is, the LCM of 6 and 12 is 12. Example 25. Find the LCM of 24 and 36. Solution. First, we find the common multiples of 24 and 36. Multiples of 24 are 24, 48, 72, 96, 120, 144 and so on. Multiples of 36 are 36, 72, 108, 144 and so on. The least or lowest common multiple of 24 and 36 is 72. Hence, the LCM of 24 and 36 is 72. Multiple choice questions, MCQs. Chapter 4. Integers. Use of integers in our daily life. We use integers in our daily life in many situations. Some of them are given below. Profit, loss. Profit is denoted by a positive integer and loss is denoted by a negative integer. For example, profit of 100 rupees equal to plus 100 rupees and loss of 100 rupees equal to minus 100 rupees. Temperature, increase, decrease. Temperature above 0 degrees Celsius is denoted by a positive integer and temperature below 0 degrees Celsius is denoted by a negative integer. For example, temperature of Leh equal to below 5 degrees Celsius equal to minus 5 degrees Celsius. Direction east-west or north-south. If we consider the distance travelled 5 km towards the east as positive, then 5 km towards the west means minus 5 km. Similarly, if the distance travelled towards the north is considered as positive, then the distance travelled towards the south will be considered as negative. Height, depth. Height is denoted by a positive integer and depth is denoted by a negative integer. This implies that a height of 500 meter above the sea level is written as 500 meter, while the depth of 500 meter below the sea level is represented as minus 500 meter. Representing integers on the number line. To represent integers on the number line, draw a line and mark 0 in the center of the line. Now mark 1, 2, 3, 4 and so on at equal distances on the right of 0. And minus 1, minus 2, minus 3, minus 4 and so on at similar distance on the left of 0. Numbers on the right side of 0 are called positive integers and the numbers on the left side of 0 are called negative integers. In this way, we can represent every integer on the number line. Here we note that 1 and minus 1, 2 and minus 2, 3 and minus 3, etc. all are at equal distances from 0, but on the opposite sides. These are called opposites or negatives of each other. Comparison of integers. Observe the following number line of integers. In the above number line, we can see that the value of numbers increases when we move towards the right, and the value of numbers decreases when we move towards left. So we can say that minus 6 is less than minus 5, which is less than minus 4, which is less than minus 3, which is less than minus 2, which is less than minus 1, which is less than 0, which is less than 1, which is less than 2, which is less than 3, which is less than 4, which is less than 5, which is less than 6. In general, we get the following results. Every positive integer is greater than every negative integer. 0 is less than every positive integer and greater than every negative integer. If x and y are two integers such that x is greater than y, then minus x is less than minus y. If x is less than y, then minus x is greater than minus y. Ordering of integers. We have learned to compare integers. Arranging them from the smallest to the greatest is known as ascending order, and arranging them from the greatest to the smallest is known as descending order. Example 1. Arrange the following numbers in ascending and descending order. Minus 5, 0, minus 7, 10, minus 3, minus 1, 5. Solution. The smallest integer is minus 7. Arranging these numbers from the smallest to the greatest, we get minus 7, which is less than minus 5, which is less than minus 3, which is less than minus 1, which is less than 0, which is less than 5, which is less than 10. Ascending order. Now arranging these numbers from the greatest to the smallest, we get 10, which is greater than 5, which is greater than 0, which is greater than minus 1, which is greater than minus 3, which is greater than minus 5, which is greater than minus 7. Descending order. Absolute value of integers. The absolute value of an integer is its numerical value regardless of its sign. Absolute value of an integer is written by putting two vertical lines on either side of the integer. For examples, absolute value of plus 9 equal to absolute value plus 9. Absolute value equal to 9. Absolute value of minus 9 equal to absolute value of minus 9 equal to 9. Absolute value of plus 12 equal to 12. Absolute value of minus 6 equal to 6. Thus, from the above examples, we conclude that if a is any integer, then absolute value of a equal to a. If a is positive or 0, absolute value of minus a equal to a. If a is negative. Example 2. Represent the following integers on a number line. A 4, b minus 8, c 7, d minus 1, e 3. Solution. Draw a number line and mark A, B, C, D and E for 4, minus 8, 7, minus 1 and 3 respectively. Example 3. Using the number line, write the integer which is A 2 more than 3, B 5 more than minus 2, C 5 less than 6, D 3 less than minus 4. Solution. A. To find the integer 2 more than 3, we start from 3 and move 2 steps to the right as shown. Doing so, we reach at 5. Thus, 2 more than 3 is 5. B. To find the integer 5 more than -2, we start from -2 and move 5 steps to the right. Doing so, we reach at 3. Thus, 5 more than -2 is 3. C. To find the integer less than 6, we start from 6 and move 5 steps to the left. Doing so, we reach at 1. Thus, 5 less than 6 is 1. D. To find integer 3 less than -4, we start from -4 and move 3 steps to the left. Doing so, we reach at -7. Thus, 3 less than -4 is -7. Example 4. Which number is smaller in each of the following? A. 0, -6. B. -10, -15. C. 310 and -256. Solution. A. 0, -6. We know that -6 is at the left of 0 on the number line. So, -6 is less than 0. B. -10, -15. On the number line, -15 is at the left of -10. So, -15 is less than -10. C. 310 and -256. We know that negative integer is smaller than positive integer. So, -256 is less than 310. Example 5. Write the absolute value of each of the following. A. -17. B. -36. C. 0. D. 15. Solution. The absolute value of A. -17 is absolute value of -17 equal to 17. B. -36 is absolute value of -36 is equal to 36. C. 0 is absolute value of 0 is equal to 0. D. 15 is absolute value of 15 is equal to 15. Write the opposites of the following. Compare the following pairs of numbers using greater than, less than, or equal to. Addition of integers. Addition of integers can be understood with the help of a number line. Adding a negative integer means moving to the left and adding a positive integer means moving to the right on the number line. Adding two positive integers. Let us add 3 and 5 on the number line. To do so, we begin with 0 and move 3 units to the right and reach P, which represents 3. Now 5 is also a positive integer, so we move 5 steps to the right from point P to reach point Q. Point Q represents 8, so 3 plus 5 equal to 8. Adding two negative integers. Let us add -3 and -4 on the number line. To do so, we begin with 0 and move 3 units to the left of 0 and reach A, which represents -3. Now -4 is also a negative integer, so we move 4 steps to the left from point A to reach point B. Point B represents -7, so -4 plus -3 equal to -7. Adding a positive and a negative integer. Let us add 5 and -6 on the number line. To do so, we begin with 0 and move 5 units to the right of 0 and reach R, which represents 5. Now we move 6 units to the left of R and reach point S. Point S represents -1, so 5 plus -6 equal to -1. Rules for addition of integers. The sum of two positive integers is the sum of their absolute values with plus sign attached to it. The sum of two negative integers is the sum of their absolute values with minus sign attached to it. The sum of a positive and a negative integer is the difference of their absolute values with the sign of the integer of greater absolute value. Example 6. Add the following integers on the number line. A minus 4 plus minus 3. B minus 6 plus 4. Solution. A minus 4 plus minus 3. B represents minus 7, so minus 4 plus minus 3 equal to minus 7. B minus 6 plus 4. Q represents minus 2, so minus 6 plus 4 equal to minus 2. Properties of addition of integers. If A and B are any two integers, then A plus B is also an integer. For example, minus 15 plus 12 equal to minus 3, which is an integer. This is called closure property of addition of integers. If A and B are any two integers, then A plus B equal to B plus A. For example, minus 5 plus minus 12 equal to minus 12 plus minus 5 equal to minus 17. This is called commutative property of addition of integers. If A, B and C are any three integers, then A plus B plus C equal to A plus B plus C. For example, minus 5 plus 7 minus 3 equal to minus 5 plus 7 minus 3. 2 minus 3 equal to minus 5 plus 4. Minus 1 equal to minus 1. This is called associative property of addition of integers. Additive inverse. If A is an integer, then A plus minus A equal to 0. For example, if A equal to 7, then 7 plus minus 7 equal to 0. A and minus A are said to be the additive inverse of each other. In above example, additive inverse of 7 is minus 7, and additive inverse of minus 7 is 7. State whether the following statements are true or false. Find the additive inverse of the following. Subtraction of integers. We have learned how to subtract a whole number from the others. We also know that subtraction is an inverse process of addition. For example, subtracting 3 from 4 is same as to find a number which when added to 3 gives 4. Clearly the number is 1. The same idea is extended to subtraction of integers. Let us now subtract two integers with the help of a number line. For example, subtract minus 3 from 8. First of all, draw a number line and arrive at point A, which represents minus 3. In order to subtract minus 3 from 8, we count steps required to reach 8 ahead from point A. We see that the number of steps required to arrive at 8 from minus 3 is 11. Name this point B. The total steps from A to B are 11. That is 8 minus minus 3 equal to 11. Also 8 plus 3 equal to 11. So 8 minus minus 3 equal to 8 plus 3 equal to 11. Remember, to subtract a positive integer, move to the left on the number line. To subtract a negative integer, move to the right on the number line. Rules for subtraction. If A and B are two integers, then to subtract B from A, we change the sign of B and add it to A. That is, A minus B equal to A plus minus B. Example 10. Subtract A minus 5 from 12, B minus 7 from minus 4, C minus 6 from 13. Solution A. To subtract minus 5 from 12, we change the sign of 5 and add it to 12. So 12 minus minus 5 equal to 12 plus 5 equal to 17. B. To subtract minus 7 from minus 4, we change the sign of 7 and add it to minus 4. So, minus 4 minus minus 7 equal to minus 4 plus 7 equal to 3. C. To subtract minus 6 from 13, we change the sign of 6 and add it to 13. 13 minus minus 6 equal to 13 plus 6 equal to 19. Properties of subtraction of integers. If a and b are any two integers and if a minus b equal to c, then c is also an integer. For example, 3 minus 4 equal to minus 1, which is also an integer. This is called closure property of subtraction of integers. Simplification of an expression involving both addition and subtraction. To simplify an expression with plus and minus signs, we follow these steps. Add all the terms with plus sign together and all the terms with minus sign together. Find the difference of the absolute values of the two sums so obtained. Assign the sign of the sum having larger absolute value to the result. For example, 7 minus 5 plus 4 plus 3 minus 2 minus 6 minus 8 equal to 7 plus 4 plus 3 minus 5 minus 2 minus 6 minus 8 equal to 14 minus 21 equal to minus 7. Example 11. Find the value of a minus 16 minus minus 24 plus minus 9 minus 4, b minus 15 plus minus 5 minus minus 10, c minus 16 plus 31 minus 30 plus 52. Solution a minus 16 minus minus 24 plus minus 9 minus 4 equal to minus 16 minus minus 24 minus 9 minus 4 equal to minus 16 minus minus 37 equal to minus 16 plus 37 equal to 21. B minus 15 plus minus 5 minus minus 10 equal to minus 15 plus minus 5 plus 10 equal to minus 15 plus 5 equal to minus 15 plus 5 equal to minus 10. C minus 16 plus 31 minus 30 plus 52 equal to minus 16 minus 30 plus 31 plus 52 equal to minus 46 plus 83 equal to 37. Example 12. Subtract the sum of minus 1740 from minus 214. Solution. Sum of minus 1740 equal to minus 1000 plus 740 equal to minus 260. Now we subtract minus 260 from minus 214. Minus 214 minus minus 260 equal to minus 214 plus 260 equal to 46. Example 13. Find the value of 412 plus minus 98 plus minus 84 plus minus 7 plus 35. Solution. 412 plus minus 98 plus minus 84 plus minus 7 plus 35 equal to 412 plus 35 plus minus 98 plus minus 84 plus minus 7. Separating plus and minus sign equal to 447 plus minus 189 equal to 447 minus 189 equal to 258. Example 14. The sum of two integers is minus 15. If one of them is minus 8, what is the other one? Solution. Sum of two integers equal to minus 15. One of the integers equal to minus 8. Other equal to what? The other integer equal to sum of two integers minus given integer equal to minus 15 minus minus 8 equal to minus 15 plus 8 equal to minus 7. Note: the commutative and associative property do not hold good for subtraction of integers. Multiple choice questions, MCQs. Tick the correct answer. Chapter 5. Fractions. Fraction as a part of whole. Let us take a fraction, say 8 upon 15. This fraction is read as 8/15th, which means that 8 parts out of 15 equal parts in which the whole is divided. In the fraction 8 upon 15, 8 is called the numerator and 15 is called the denominator. To understand better, look at the table shown below. Figure, fraction, numerator, denominator. 3 upon 7, 3/7, 3, 7. 5 upon 11, 5/11, 5, 11. 2 upon 5, 2/5, 2, 5. 7 upon 8, 7/8, 7, 8. 9 upon 10, 9/10, 9, 10. Fraction as a part of collection. Study the following collections. 5 upon 7, 7 upon 15, 3 upon 10. In the above figures, we can see that the collections are divided in parts. The fraction obtained after separation is called fraction as a part of collection. Complete the following table by writing the numerators and denominators of the given fractions. Representation of fractions on the number line. Let's represent 3 upon 5 on a number line. To show 3 upon 5 on a number line, follow the given steps. Step 1. Draw a line and mark the point A representing 0. Step 2. Since the denominator is 5, mark 5 points 1 upon 5, 2 upon 5, 3 upon 5, 4 upon 5 and 5 upon 5 starting from 0 at equal distances towards the right. Step 3. Point A represents 0, C represents 1 upon 5, D 2 upon 5, E 3 upon 5, F 4 upon 5 and B represents 5 upon 5 or 1. Step 4. Encircle the point 3 upon 5. Can you show 0 upon 5 and 5 upon 5 on the number line in the above example? Yes, 0 upon 5 and 5 upon 5 can be shown on the number line because 0 upon 5 is 0, which is point A, and 5 upon 5 is 1, which is point B. There are infinite fractions between two numbers. Conversion of fractions. Conversion of improper fractions into mixed fractions. Let us consider an improper fraction, say 49 upon 5. Divide the numerator by the denominator to obtain the quotient and the remainder. Here 49 divided by 5 gives quotient equal to 9, remainder equal to 4. The quotient will be the whole number and the remainder will be the numerator of the proper fraction. Write the denominator as it is. So, 49 upon 5 equal to 9, 4 upon 5. Thus, mixed fraction equal to quotient, remainder upon denominator. Conversion of mixed fractions into improper fractions. Consider a mixed fraction, say 3, 1 upon 5. Multiply the whole number by the denominator of the proper fraction, 3 into 5 equal to 15. Add the numerator to the obtained product, 15 plus 1 equal to 16. Write the fraction with new numerator obtained in step 3 and the denominator as it is, that is 3, 1 upon 5, equal to 3 into 5 plus 1 upon 5, equal to 15 plus 1 upon 5, equal to 16 upon 5. Thus, improper fraction equal to whole number into denominator plus numerator upon denominator. Note, the value of a proper fraction is always less than 1 and the value of an improper fraction is always greater than 1. Equivalent fractions. Look at the following figures carefully. Have you observed that the shaded parts represented by the fractions 1 upon 2, 2 upon 4, 3 upon 6 and 4 upon 8 are equal? Yes, since all shaded parts cover the same area, this means these fractions represent the same part of a whole, that is 1 upon 2 equal to 2 upon 4 equal to 3 upon 6 equal to 4 upon 8. We say the above fractions are equivalent fractions. Equivalent fractions are those which have the same value. Have a close look at the above fractions. 1 upon 2 equal to 2 upon 4 equal to 3 upon 6 equal to 4 upon 8. We have 1 upon 2 equal to 1 into 2 upon 2 into 2 equal to 2 upon 4, or 1 into 3 upon 2 into 3 equal to 3 upon 6, or 1 into 4 upon 2 into 4 equal to 4 upon 8. This means that by multiplying the numerator and denominator of a fraction by the same number, we get an equivalent fraction, that is a fraction with the same value. Similarly, if we divide the numerator and denominator by the same number, the value will remain the same. For example, 4 upon 8 equal to 4 upon 8 divided by 2 upon 2 equal to 2 upon 4, which is divided by 2 upon 2 equal to 1 upon 2, or 3 upon 6 equal to 3 upon 6 divided by 3 upon 3 equal to 1 upon 2. Remember, equivalent fractions represent the same part of a whole. By multiplying the numerator and denominator with the same non-zero number, the value of fraction does not change. By dividing the numerator and denominator with the same non-zero number, we obtain an equivalent fraction. An interesting fact about equivalent fractions. When two fractions are equivalent, they show the following fact. Numerator of first fraction into denominator of second fraction equal to denominator of first fraction into numerator of second fraction. Example 1. Check whether 3 upon 10 and 15 upon 50 are equivalent fractions or not. Solution. Cross multiply 3 upon 10 and 15 upon 50. That is 3 upon 10 cross multiplication with 15 upon 50. We have 3 into 50 equal to 150 and 10 into 15 equal to 150. Since both the products are the same, the given fractions are equivalent. Comparison of fractions. Comparison of like fractions. As the like fractions have the same denominator, we need to consider only their numerators to compare them. Greater the numerator, greater will be the fraction. For example, 2 upon 3 is greater than 1 upon 3, as 2 is greater than 1. Comparison of unlike fractions. In order to compare unlike fractions, first we convert them into like fractions by using the following steps and then compare them. Obtain the denominators of the fractions and find their LCM. Convert each fraction to its equivalent fraction with denominator equal to LCM obtained in step 1. Compare the numerators of the equivalent like fractions. Example 9. Which fraction is bigger, 3 upon 8 or 5 upon 16? Solution. Let us find the LCM of 8 and 16. LCM of 8 and 16 equal to 2 into 2 into 2 into 2 equal to 16. Now we convert the given fractions into equivalent fractions with denominator 16. 3 upon 8 equal to 3 upon 8 into 2 upon 2 equal to 6 upon 16. 5 upon 16 equal to 5 upon 16 into 1 upon 1 equal to 5 upon 16. We observe that 6 is greater than 5, so 6 upon 16 is greater than 5 upon 16, or 3 upon 8 is greater than 5 upon 16. Ordering of fractions. Arranging fractions from the smallest to the greatest is known as ascending order, while arranging fractions from the greatest to the smallest is known as descending order. Ordering of like fractions. Example, arrange 2 upon 7, 1 upon 7, 5 upon 7, 4 upon 7 in ascending and descending order. Solution. 1 upon 7 is less than 2 upon 7, which is less than 4 upon 7, which is less than 5 upon 7, ascending order. 5 upon 7 is greater than 4 upon 7, which is greater than 2 upon 7, which is greater than 1 upon 7, descending order. Ordering of unlike fractions. To order unlike fractions, first we find the LCM of the denominators of given fractions and change them into like fractions. Finally, we order them. Example, arrange 2 upon 3, 4 upon 5, 3 upon 6, 1 upon 3 in ascending and descending order. Solution. Since denominators are different, we find the LCM of 3, 5 and 6. LCM of 3, 5 and 6 is 30. Now 2 upon 3 equal to 2 upon 3 into 10 upon 10 equal to 20 upon 30. 4 upon 5 equal to 4 upon 5 into 6 upon 6 equal to 24 upon 30. 3 upon 6 equal to 3 upon 6 into 5 upon 5 equal to 15 upon 30. 1 upon 3 equal to 1 upon 3 into 10 upon 10 equal to 10 upon 30. Clearly, 10 upon 30 is less than 15 upon 30, which is less than 20 upon 30, which is less than 24 upon 30. Or 1 upon 3 is less than 3 upon 6, which is less than 2 upon 3, which is less than 4 upon 5, ascending order. And 4 upon 5 is greater than 2 upon 3, which is greater than 3 upon 6, which is greater than 1 upon 3, descending order. Circle the like fractions in each group. Which of the following are unit fractions? Compare the following fractions by putting an appropriate sign, less than, greater than, or equal to. Addition of fractions. Addition of like fractions. To add like fractions, we simply add the numerators of both the fractions and write the denominator as it is. Example 15. Add A. 3 upon 4 and 5 upon 4. B. 3 upon 16, 5 upon 16 and 6 upon 16. Solution A. 3 upon 4 plus 5 upon 4 equal to 3 plus 5 upon 4 equal to 8 upon 4 equal to 2. B. 3 upon 16 plus 5 upon 16 plus 6 upon 16 equal to 3 plus 5 plus 6 upon 16 equal to 14 upon 16 equal to 7 upon 8. Addition of unlike fractions. We know that unlike fractions are those in which denominators are different. Example 3 upon 4, 5 upon 6, 6 upon 7, etc. are unlike fractions. To add unlike fractions, first convert them into equivalent fractions with same denominator, then add. Example 16. Add 9 upon 16 and 5 upon 12. Solution. LCM of 16 and 12 equal to 48. LCM equal to 2 into 2 into 2 into 2 into 3 equal to 48. Now 9 upon 16 equal to 9 upon 16 into 3 upon 3 equal to 27 upon 48. 5 upon 12 equal to 5 upon 12 into 4 upon 4 equal to 20 upon 48. So 27 upon 48 plus 20 upon 48 equal to 27 plus 20 upon 48 equal to 47 upon 48. Subtraction of fractions. Subtraction of like fractions. The method for subtraction of like fractions is similar to that of their addition. As the denominators of like fractions are same, we subtract the smaller numerator from the greater one. For example, 15 upon 7 minus 6 upon 7 equal to 15 minus 6 upon 7 equal to 9 upon 7. Subtraction of unlike fractions. Subtraction of unlike fractions is also carried out in the same manner as their addition. First, unlike fractions are converted into equivalent fractions having a common denominator. Then they are subtracted. For example, 17 upon 10 minus 3 upon 2 equal to 17 upon 10 minus 3 upon 2 into 5 upon 5. LCM of 10, 2 equal to 10. Equal to 17 upon 10 minus 15 upon 10 equal to 17 minus 15 upon 10 equal to 2 upon 10 equal to 1 upon 5. Subtraction of mixed fractions. Subtraction of mixed fractions is similar to the addition of mixed fractions. Example 21. Find the difference between 3, 4 upon 5 and 1, 1 upon 4. Solution. 3, 4 upon 5 minus 1, 1 upon 4 equal to 19 upon 5 minus 5 upon 4. LCM of 5 and 4 is equal to 20. Now 19 upon 5 equal to 19 upon 5 into 4 upon 4 equal to 76 upon 20. 5 upon 4 equal to 5 upon 4 into 5 upon 5 equal to 25 upon 20. So, 76 upon 20 minus 25 upon 20 equal to 76 minus 25 upon 20 equal to 51 upon 20 equal to 2, 11 upon 20. Multiple choice questions, MCQs. Chapter 6. Decimals. Decimals. A decimal consists of two parts, a whole number part and a decimal part, separated by a decimal point. For example, whole number part 235, point, decimal point, 493, decimal part. Following are a few examples of the use of decimals in our daily life. Height of a person equal to 1.6 meter. Temperature of human body equal to 98.6 degree Fahrenheit. Length of long jump by an athlete equal to 3.12 meter. Time to complete a swimming event equal to 1.32 second. Dose of medicine given to an infant equal to 2.5 milliliter. Decimals are used as they are easy to add, subtract, multiply, divide, compare, and express. Decimal fractions with 10 as denominator. Fractions having 10 as denominator are called tenths. Some of the examples are given below. Shaded part, decimal fraction, decimal number, read as 1 upon 10 or 1/10, 0.1. 2 upon 10 or 2/10, 0.2. 3 upon 10 or 3/10, 0.3. 5 upon 10 or 5/10, 0.5. Decimal fractions with 100 as denominator. Fractions having 100 as denominator are called hundredths. Some of the examples are given below. Shaded part, decimal fraction, decimal number, read as 1 upon 100 or 1/100th, 0.01, 0.01. 2 upon 100 or 2/100th, 0.02, 0.02. 3 upon 100 or 3/100th, 0.03, 0.03. Decimal fractions with 1000 as denominator. Fractions having 1000 as denominator are called thousandths. Some of the examples are given below. Shaded part, decimal fraction, decimal number, read as 1 upon 1000 or 1000th, 0.001, 0.001, 4 upon 1000 or 4000th, 0.004, 0.004, 89 upon 1000 or 89,000th, 0.089, 0.089. Representation of decimals on the number line. As we represent fractions on the number line, in the same way we can represent decimals on the number line. Let us try to represent 0.6 on the number line. We know that 0.6 lies between 0 and 1. So we divide the distance between 0 and 1 into 10 equal parts. Point P represents 0.6. Let us now represent 2.3 on the number line. 2.3 means 2 whole and 0.3. So it lies between 2 and 3. 2.3 means 23 upon 10. So divide the distance between 2 and 3 into 10 equal parts as shown below. Point Q represents 2.3. Example 1. Write the following decimals in the decimal place value chart. A. 3.16, B. 12.427, C. 372.99. Solution: hundreds, tens, ones, point, tenths, hundreds, thousands. 3.16, 12.427, 372.99. Example 2. Write the place value of each digit of 349.625 and then write in expanded form. Solution: arranging the digits of the given number in place value chart, we have hundreds, tens, ones, point, tenths, hundreds, thousands. 349.625. Now, place value 5 upon 1000 or 0.005 or 5000. 2 upon 100 or 0.02 or 200. 6 upon 10 or 0.6 or 6 tenths. 9 into 1 equal to 9. 4 into 10 equal to 40. 3 into 100 equal to 300. Expanded form: 349.625 equal to 300 plus 40 plus 9 plus 6 upon 10 plus 2 upon 100 plus 5 upon 1000, or 300 plus 40 plus 9 plus 0.6 plus 0.02 plus 0.005, or 300 plus 40 plus 9 plus 6 tenths plus 200 plus 5000. Remember, expanded form is the representation of the number as the sum of the place values of all its digits. Example 3. Write the following in expanded form. A. 2.75, B. 25.004. Solution: A. 2.75 equal to 2 plus 7 upon 10 plus 5 upon 100, or 2 plus 0.7 plus 0.05. B. 25.004 equal to 20 plus 5 plus 4 upon 1000, or 20 plus 5 plus 0.004. Example 4. Write the decimal numbers and number names for the following. A. 20 38 upon 100. B. 315 652 upon 100. C. 5 8 upon 100. D. 6 4 upon 1000. Solution: decimal number name: 20 38 upon 100, 20.38, 20.38, 315 65 upon 100, 315.65, 315.65, 5.8 upon 100, 5.08, 5.08, 6, 4 upon 1000, 6.004, 6.004. Express the following as decimals. Write the following in decimals form. Express the following decimals in their expanded form. Conversion of fractions into decimals and vice versa. Conversion of fractions into decimals. To convert a fraction with denominator 10, 100 or 1000 into decimals, write the numerator and mark the decimal point after one place or two places or three places as required from the right. Example, 13 upon 10 equal to 1.3. 259 upon 100 equal to 2.59. 312 upon 1000 equal to 0.312. But we also come across the cases where the denominator of the fraction is neither 10 nor a power of 10. In such cases, we first convert the given fraction into an equivalent fraction with denominator 10 or a power of 10. Example, 5 upon 2 equal to 5 upon 2 into 5 upon 5 equal to 25 upon 10 equal to 2.5. 1. 3 upon 4 equal to 7 upon 4 equal to 7 upon 4 into 25 upon 25 equal to 175 upon 100 equal to 1.75. 1 upon 8 equal to 1 upon 8 into 125 upon 125 equal to 125 upon 1000 equal to 0.125. 3 upon 250 equal to 3 upon 250 into 4 upon 4 equal to 12 upon 1000 equal to 0.012. Conversion of decimals into fractions. To convert a decimal into fraction, remove the decimal point from the given decimal, and the number thus obtained becomes the numerator of the common fraction. The denominator is formed by putting 1 followed by the number of zeros equal to the number of digits at the right of the decimal point in the given decimal fraction. Observe the following examples. 0.25 equal to 0.25 upon 100 equal to 25 upon 100. There are two digits after decimal, so the denominator would have two zeros followed by 1. 0.6 equal to 0.6 upon 10 equal to 6 upon 10. There is one digit after decimal, so the denominator would contain one zero followed by 1. 1.732 equal to 1732 upon 1000. There are three digits after decimal, so the denominator would contain three zeros after 1. Equivalent decimals. Let us compare the fractions 1 upon 10, 10 upon 100, and 100 upon 1000. On simplification, we get 100 upon 1000 equal to 1 upon 10, and 10 upon 100 equal to 1 upon 10. Thus, we see that 1 upon 10 equal to 10 upon 100 equal to 100 upon 1000. These are called equivalent fractions. Writing these fractions in their decimal form, we have 1 upon 10 equal to 0.1. 10 upon 100 equal to 0.10. 100 upon 1000 equal to 0.100. So 0.1, 0.10 and 0.100 are called equivalent decimals. Now let's compare 600 upon 1000, 60 upon 100 and 6 upon 10. On simplification, we get 600 upon 1000 equal to 6 upon 10 and 60 upon 100 equal to 6 upon 10. Thus we see that 600 upon 1000 equal to 60 upon 100 equal to 6 upon 10. But 600 upon 1000 equal to 0.600. 60 upon 1000 equal to 0.60. 6 upon 10 equal to 0.6. Therefore 0.600 equal to 0.60 equal to 0.6. Thus, addition of any number of 0 after the extreme right digit in the decimal part of a decimal number does not change the value of the number. Comparing decimals. To compare two decimals, first convert the given decimals into like decimals required and then follow these steps. First, compare the whole number parts of the given decimals. The decimal with greater whole number part is greater. If the whole number parts are equal, then go to the next step. Compare the tens digits of the given decimals. The decimal with the greater digit at tens place will be greater. If the tens digit are equal, then go to the next step. Now compare the hundredths digits. The decimal with bigger hundredths digit will be greater. If the hundredths digits are also equal, then compare the thousandths digit and so on. Example, compare 32.45 and 43.63. On comparing whole number parts, we get 32 less than 43 or 43 is greater than 32. So 43.63 is greater than 32.45. Compare 2.34 and 2.12. On comparing whole number parts, we find that 2 equal to 2. Now comparing the tens digits, we get 3 greater than 1. Hence, 2.34 is greater than 2.12. Ordering of decimals. So far we have learned to compare decimals. Now we will learn to arrange them in ascending and descending order. Let us arrange the following decimals in ascending and descending order. 8.6, 2.34, 1.10, 6.59, 3.003. We first convert all the decimals into like decimals as shown below. 8.600, 2.340, 1.100, 6.590, 3.003. Now, 1.100 is less than 2.340, which is less than 3.003, which is less than 6.590, which is less than 8.600, ascending order. Now, 8.600 is greater than 6.590, which is greater than 3.003, which is greater than 2.340, which is greater than 1.100, descending order. Example 5. Convert the following decimals into fractions. A. 3.52. B. 14.09. Solution. A. 3.52 equal to 352 upon 100. 352 upon 100 divided by 2 upon 2 equal to 176 upon 50. 176 upon 50 divided by 2 upon 2 equal to 88 upon 25. B. 14.09 equal to 1409 upon 100. Example 6. Convert the following fractions into decimals. A. 2, 1 upon 25. B. 19 upon 20. Solution. A. 2, 1 upon 25 equal to 51 upon 25 equal to 51 upon 25 into 4 upon 4 equal to 204 upon 100 equal to 2.04. B. 19 upon 20 equal to 19 upon 20 into 5 upon 5 equal to 95 upon 100 equal to 0.95. Addition of decimals. To add the decimals, we proceed in the following manner. Convert the given decimals into like decimals. Write the decimals one below the other so that the decimal points of all the decimals are in the same column, or the digits having the same place values should be in the same column. Add in the same way as we add the whole numbers. Put the decimal point exactly below the decimal point in the answer. Example 9. Add 42.14, 18.896 and 362.73. Solution. Converting the given decimals into like fractions, we get 42.140, 18.896, 362.730. Thus the sum is 423.766. Example 10. Subject-wise marks obtained by Vishnu in a competition exam are as under: Science 76.75, Maths 95.50, English 67.25, Social Science 62.50. What is the total of marks obtained by him? Solution. Marks obtained in Science equal to 76.75. Marks obtained in Maths equal to 95.50. Marks obtained in English equal to 67.25. Marks obtained in Social Science equal to plus 62.50. Total marks obtained equal to 302.00. Subtraction of decimals. To subtract one decimal number from the other, we proceed in the following manner. Step 1. Convert the given decimals into like decimals. Step 2. Place the decimal point exactly below the other decimal point. Step 3. Subtract column-wise and put decimal point in the answer exactly below the decimal points of the numbers. Example 11. Subtract 4.36 from 9.58. Solution. Thus, 9.58 minus 4.36 equal to 5.22. Example 12. Subtract 1987.45 from 2416.026. Solution. Thus, 2416.026 minus 1987.45 equal to 428.576. Example 13. A water tank contains 500 liters of water. On Monday, 236.54 liters of water is pumped out. Find the amount of water left in the tank. Solution. Total water in the tank equal to 500.00 liter. Water pumped out of the tank equal to 236.54 liter. Amount of water left in the tank equal to 500.00 minus 236.54 equal to 263.46 liter. Hence the remaining water inside the tank is 263.46 liter. Which of the following are groups of like decimals? Multiple choice questions, MCQs. Chapter 7. Introduction to Algebra. Algebraic expressions. A combination of constants and variables connected by the symbol plus, minus, multiply or divide is called an algebraic expression. The various parts of the algebraic expression reported by the sign plus or minus are called the terms of the expression. For example, 2x plus 3y minus 5xy is an algebraic expression in which 2x, 3y and minus 5xy are the terms. Forming expressions. Using only letters and signs, we can write the expression for the statement given. Statement, expression. 6 subtracted from x, x minus 6. 2 subtracted from the sum of x and y, x plus y minus 2. Similarly, we can write the statement for algebraic expressions as given below. Expression, statement. Y divided by 8, number y divided by 8. 2z minus 4. 4 is subtracted from the product of 2 and z. Coefficient of algebraic terms. Any factor of a term is called the coefficient of the product of the remaining factors. Let's observe the algebraic terms 2x, 7y, 9xy and 4abc. These terms contain a variable part and a numerical part, while the literals such as x, y, xy, abc, etc. are the variable components of the terms. The numerical 2, 7, 9 and 4 are the numerical coefficients of the terms. Even if there is no numerical number before a variable term for x, ab or abc, we consider the numerical coefficient of these terms as 1. That is, x equal to 1x, ab equal to 1ab and so on. In the algebraic term 5xyz, 5 is the coefficient of xyz. 5x is the coefficient of yz, 5xy is the coefficient of z, and so on. Note, if it is not specified what or whose coefficient is to be written, always mention the numerical coefficient. Like and unlike terms. Two or more terms are like terms when the variables and their powers are identical. For example, 3m and 18m are like terms. Similarly, 2xy, 15xy and minus 87xy are like terms. Also, 40a square b and 20a square b are like terms. Unlike terms will have different variables or variables with different powers. 5ac, 5a square c are examples of unlike terms. Similarly, other examples of unlike terms are a cube, ac. Like terms can be added or subtracted to get a single term, just as 3a square b plus 6a square b plus 7a square b equal to 16a square b and 9ab square minus 4ab square equal to 5ab square. In the case of unlike terms, 4a square b plus 4ab square equal to 4a square b plus 4ab square. Example 5. Categorize the following into like and unlike terms. 1. A cube, ac, 5a cube, a raised to the power 6, 45a cube. 2. 3a square bc, 3abc, 6a square b, 5a square bc, 8a square bc, and 8a square b square c. Solution, like terms. A cube, 5a cube, 45a cube. Unlike terms, ac, a raised to the power 6. Like terms, 3a square bc, 5a square bc, 8a square bc. Unlike terms, 3abc, 6a square b, 8a square b square c. Categorize each of the following as a set of like terms or unlike terms. Terms of an expression. We know that the several parts of an expression connected by plus or minus are called terms of the expression. Thus, in the expression 4x plus 3y, 4x and 3y are the terms. The sign along with the term is important. If we have an expression 7xy minus 4yz plus 5zx, then 7xy minus 4yz and 5zx are the terms of the expression. Notice that the terms are separated by plus and minus only. Thus in 3xy is a single term, while in x plus 2y, x and 2y are two terms. Monomial, an expression consisting of one term, is a monomial. Thus 2xy, 5x and 30 are all examples of monomials. Binomial, an expression consisting of two terms, is a binomial. Thus x minus y, 2a plus b and 5xy plus 3yz, 5x minus 3 are all binomials. Trinomial, an expression consisting of three terms is called a trinomial. Thus, 3x plus 4y minus z, 5xy plus 4yz plus 3 and a plus b minus c are examples of trinomials. Polynomial, expressions consisting of several terms, two or more, are called multinomials or polynomials. The expression 5x plus 6y minus 2z plus 4 is an example of a polynomial. Factor, when two or more numbers, arithmetic or literal, are multiplied, the result is called the product. Each number that has been multiplied to get the product is a factor. Consider 10ab. 10ab equal to 2 into 5 into a into b. So 2, 5, a, b, 2a, 2b, 5a, 5b, 5ab, 2ab and so on are factors of 10ab. 2, 5 equal to numerical factors. A, b, ab are the literal or variable factors. Example 6. Express the following as algebraic expressions. A. Sum of two consecutive numbers is 15. B. 5 is added to the product of two consecutive numbers. Solution. A. Let x be any number, successor of x equal to x plus 1. Now x and x plus 1 are two consecutive numbers. Therefore, the required expression is x plus 1 equal to 15 or 2x plus 1 equal to 15. B. Let x and x plus 1 be two consecutive numbers. 5 added to the product of x and x plus 1 is x into x plus 1 plus 5. State which of the following are monomials, binomials and trinomials. Algebra as generalization. Generalized form of algebra can be used to solve a variety of mathematical problems. When we say that the perimeter of a rectangle is equal to 2 into L plus B, or the area of a rectangular surface is L into B, where L stands for the length of the rectangle and B stands for its breadth, we have a general formula which can be used to determine the perimeter and area of any rectangular surface. This generalization is true for any rectangle irrespective of the numerical values of length and breadth. Look at the number series 1, 5, 9, 13, 17, 21. 1 equal to 4 into 1 minus 3. 5 equal to 4 into 2 minus 3. 9 equal to 4 into 3 minus 3. 13 equal to 4 into 4 minus 3. 17 equal to 4 into 5 minus 3. 21 equal to 4 into 6 minus 3. Therefore, in general, the formula is 4x minus 3. A careful observation will give us the general formula for the terms as 4x minus 3. Once you get this general formula, we can find any term in the number series. For example, 7th term, 4 into 7 minus 3 equal to 28 minus 3 equal to 25. 10th term equal to 4 into 10 minus 3 equal to 40 minus 3 equal to 37. 100th term equal to 4 into 100 minus 3 equal to 400 minus 3 equal to 397. Look at the patterns of squares made with the matchsticks given here. Number of squares, number of matchsticks. 1, 4, 2, 7, 3, 10, 4, 13, n, 3n plus 1. If there are n squares, then the number of matchsticks will be 3n plus 1. This means that n can take any value and accordingly the number of matchsticks will be 3n plus 1. This is a generalized statement. Algebraic equations. A mathematical statement equating two quantities is called an equation. The expressions on either side of the equal to sign are called the members of the equation. In an equation, the value of the quantity which is not known is referred to as the unknown member or the unknown. Here are some examples of equations. 4x plus 5 equal to 21. A minus 2 equal to 10. Y plus 3 equal to 21. In the equation 4x plus 5 equal to 21, note that 4x plus 5 is the left-hand side member and 21 is the right-hand side member of the equation. In other words, in an equation, the terms on the left-hand side, LHS, of the equal to sign are equal to the terms on the right-hand side, RHS, of the equal to sign. Consider the equation 6x plus 5 equal to 2x plus 17. Here left-hand side LHS equal to 6x plus 5. Right-hand side RHS equal to 2x plus 17. 6x plus 5 equal to 2x plus 17. LHS equal to RHS. The equation x minus 3 equal to 8 means that when 3 is taken away from the unknown number x, we are left with 8. Look at the scales of the balance in figure. Do you find any similarity between the balance and an equation? An equation is like a weighing balance having equal weights on each pan of the balance. Both sides of the equation are balanced in the same manner as the scales of a balance. In order to maintain the balance, we need to remember the following rules. Rules: if any mass is added to one side of the balance, a corresponding mass should also be added to the other side. If any mass is taken away from one side of the balance, a corresponding mass should also be taken away from the other side. If the mass on one side is doubled, tripled, or multiplied by any number, the same must also be done to the other side. If the mass on one side is halved or divided into a certain number of equal parts, the same has to be done on the other side as well. Equations also follow these 4 rules of a balance. If we add, subtract, multiply, or divide any one side of the equation by any number, we have to do the same on the other side of the equation to keep the equation balanced. Fill in the boxes. Multiple choice questions, MCQs. Take the correct answer. Take the correct answer. Chapter 8. Ratio, Proportion and Unitary Method. Ratio. Ratio of two quantities is a fraction that tells how many times one quantity is of the other, and the two quantities should have the same unit. The colon is generally used to express a ratio. For example, we can express the fraction 5 upon 11 as 5:11, and it is read as 5:11. In general, if P and Q are two numbers, then their ratio can be written as P upon Q or P:Q, where symbol is used to represent the ratio and P and Q are the terms of the ratio. The first term P is called the antecedent and the second term Q is called the consequent of the ratio P:Q. Simplest or lowest form of a ratio. A ratio is usually written in its simplest or lowest form. For example, if Romy has 30 toffees and Rita has 45 toffees, then the ratio of toffees of Romy to that of Rita is written as 30:45. But as you can observe, 30 and 45 have a common factor, 15. Therefore, the ratio of toffees can be written as 30:45 equal to 2:3. This is the simplest form of ratio. Hence, a ratio is in its simplest form when its first and second terms have no common factor except 1. Some important points to remember about ratios. Ratio exists between two quantities of the same kind. To find the ratio between two quantities, we need to ensure that they are expressed in the same units. Ratio being a fraction has no units. The order of the term in a ratio is very important. The ratio 3 upon 5 is different from 5 upon 3. In general, P:Q is not equal to Q:P. Equivalent ratios. The ratio is similar to that of a fraction. So, like equivalent fractions, we can obtain equivalent ratios by multiplying or dividing both the antecedent and the consequent by the same non-zero number. For example, 20:50 equal to 20 upon 50 equal to 20 divided by 10 upon 50 divided by 10 equal to 2 upon 5 equal to 2:5 equal to 20 into 3 upon 50 into 3 equal to 60 upon 150 equal to 60:150 equal to 20 divided by 2 upon 50 divided by 2 equal to 10 upon 25 equal to 10:25. Thus, 2:5, 10:25 and 60:150 are equivalent ratios. Comparison of ratios. In order to compare two given ratios, we follow the given steps. Obtain the given ratios. Express each one of them in the form of a fraction in the simplest form. Now compare these fractions by making their denominators equal. Let us compare the ratios 4:5 and 3:4. We have 4:5 equal to 4 upon 5 and 3:4 equal to 3 upon 4. The LCM of 5 and 4 equal to 20. Making the denominators of each fraction equal to 20, we have 4 upon 5 equal to 4 upon 5 into 4 upon 4 equal to 16 upon 20 and 3 upon 4 equal to 3 upon 4 into 5 upon 5 equal to 15 upon 20. Clearly, 16 upon 20 is greater than 15 upon 20. Hence, 4 upon 5 is greater than 3 upon 4, or 4:5 is greater than 3:4. Example 1. Find the ratio of the following. A. 45 minutes to 5 hours. B. 25 rupees to 50 paise. Solution. A. 45 minutes to 50 hours. To find the given ratio, we convert 5 hours into minutes. 5 hours equal to 5 into 60 minutes equal to 300 minutes. Now, 45 minutes to 300 minutes equal to 45 is to 300. Equal to 45 upon 300 equal to 9 upon 60 equal to 3 upon 20 equal to 3 is to 20. B. 25 rupees to 50 paise. 50 paise equal to 50 upon 100 rupees equal to 0.5 rupees equal to 25 upon 0.5 equal to 250 upon 5 equal to 50 upon 1 equal to 50 is to 1. Find the ratio of the following. In a year, Swati earns 1,50,000 and saves 70,000. Find the ratio of. Fill in the boxes. Proportion. A proportion is a statement that shows two ratios are equal, or an equality of two ratios is called a proportion. The proportion of two or more numbers is represented by, for example, consider the two ratios 2 is to 6 and 5 is to 15. We find that 2 is to 6 equal to 1 is to 3 and 5 is to 15 equal to 1 is to 3. Therefore, 2 is to 6 equal to 5 is to 15. Thus, both the given ratios are in proportion. Similarly, 6 is to 18 and 8 is to 24 and 40 is to 70 and 200 is to 350 are in proportion. In general, 4 numbers are said to be in proportion if the ratio of the first two quantities is equal to the ratio of the last two. If 4 numbers A, B, C and D are in proportion, then we write A is to B proportion to C is to D. It is read as A is to B as C is to D. The first and the fourth term in a proportion are called the extreme terms or extremes, and the second and the third terms are called the middle terms or means. If 4 quantities are in proportion, then product of extremes is equal to product of means. That is, for 4 numbers A, B, C and D, we have A into D equal to B into C or AD equal to BC. Let us verify. Consider the following proportion. 2 is to 6 as 5 is to 15. So, 2 into 15 equal to 6 into 5. 30 equal to 30. Product of extremes equal to product of means. From this, we conclude that if AD is not equal to BC, then A, B, C, D are not in proportion. Continued proportion. 3 numbers A, B and C are said to be in continued proportion if A, B, B, C are in proportion. Thus, if A, B and C are in continued proportion, then A, B, B, C are in proportion, that is, A is to B as B is to C. We know that product of extreme terms equal to product of mean terms. So, A into C equal to B into B. AC equal to B square. Hence, B square equal to AC. Mean proportional. If A, B and C are in continued proportion, then B is called the mean proportional between A and C. So if B is the mean proportional between A and C, then B square equal to AC. Example 7. R6, 2, 9, 3 in proportion. Solution. Product of extremes equal to 6 into 3 equal to 18. Product of means equal to 2 into 9 equal to 18. Since product of extremes equal to product of means, therefore 6, 2, 9, 3 are in proportion. Fill in the box so that the four numbers are in proportion. Unitary method. Consider the following problem. Cost of 5 notebooks is 50 rupees. What will be the cost of 12 notebooks? As the cost of 5 notebooks is 50 rupees, the cost of one notebook will be lesser than 50 rupees. We can find the cost of one notebook by dividing 50 rupees by 5. The answer is 10 rupees. However, the cost of 12 notebooks will be more than the cost of one notebook. So we multiply 10 rupees by 12 and get the answer as 120 rupees. That is, 120 rupees is the cost of 12 notebooks. As it is seen in the above example, with the increase or decrease in the number of notebooks, their cost also increases or decreases in a fixed ratio is called direct variation or direct proportion. To solve a problem based on direct proportion, first we need to find the value of one item from the given total value of certain number of the same items. Then we can use this value to find the value of the required number of articles. This method is known as unitary method. The two main steps of the unitary method are: Step 1, value of one item equal to value of given number of items upon given number of items. Step 2, value of required number of items equal to value of one item into required number of items. Example 13. Cost of one school bag is 300 rupees. What will be the cost of 10 school bags? Solution. Cost of one school bag equal to 300 rupees. Cost of 10 school bags equal to 300 rupees into 10 equal to 3000 rupees. Multiple choice questions, MCQs. Chapter 9. Basic Geometrical Ideas. Point. A point is the simplest form of geometrical shapes. A point is a mark of position. It has no length, breadth, or height. It has a position and location, but no magnitude. A small dot made by a sharp pencil on a piece of paper or a tiny prick made by a fine pen or tip of the compass is the example of point. A point is denoted by capital letters such as A, B, C, D, P, Q, R, etc. Line. If the point of a pencil is moved over a sheet of paper along the edge of a ruler, the traced left represents a line. A line has length only. It has neither width nor thickness. A line can be extended infinitely in both directions along its length. It is named either by small letters L, M, N, P, Q, etc. or by using 2 points on it. Note, in the above figure, line PQ can also be written as line QP. We denote a line PQ as line PQ. Remember, a line cannot be measured as it extends infinitely in both directions. An infinite number of points lie on a line. Line segment. A line segment is a part of a line. It has 2 endpoints and a fixed length. Boundaries of a blackboard, edge of a table, edge of a paper, edge of a sari, etc. are the examples of line segments. We denote the line segment AB as line segment AB. Remember, Infinite number of lines can be drawn through a point. Types of lines. Intersecting lines. When two lines intersect each other at one point, they are called intersecting lines. The meeting point of intersecting lines is called the point of intersection. In the adjoining figure, lines L and M are intersecting lines and P is their point of intersection. A pair of scissors, English letter X, red cross sign, etc. are the examples of intersecting lines. Examples of intersecting lines. Parallel lines. A pair of straight lines which never meet each other even if they are extended infinitely are called parallel lines. The symbol of parallel lines is, in the figure shown below, line AB is parallel to line CD. We write it as line AB is parallel to line CD. Railway lines, the steps of a ladder, the opposite sides of a square, a rectangular swimming pool, etc. are the examples of parallel lines. Collinear points. 3 or more points are said to be collinear if they all lie on the same line, and the points are said to be non-collinear if all do not lie on the same line. In the given figures, points A, B, C, and D are collinear points, and P, Q, and R are non-collinear points. Remember, 2 points are always collinear. Concurrent lines. 3 or more lines are said to be concurrent if they all pass through a common point. The common point is called the point of concurrence. In the adjoining figure, lines L, M, N, and P are called concurrent lines as they pass through the same point O. Point O is called the point of concurrence. Ray. A ray is a part of a line that begins at one point and extends endlessly only in one direction. A ray is represented by an arrow. The arrow points to the direction in which the ray is extending. The figure given below shows ray PQ, and that can be denoted as ray PQ. Remember, a ray has only one endpoint. Note, ray PQ is not equal to ray QP. Sun rays, torchlight, etc. are the examples of rays. Plane. A plane is defined as a flat surface that extends indefinitely in all directions. A room has 6 planes represented by its 4 walls, floor, and ceiling. All the 6 planes of the room can be extended indefinitely. Some other examples of planes are the cover of a book, top of your dining table, surface of your carpet, etc. A plane can be denoted in 2 ways. By writing a single small letter of such as P or Q, etc. inside it, and it is read as plane P or plane Q, etc. By taking 3 different points, say A, B, and C in the plane, but not on the same line, and it is read as plane ABC. Example 1. Identify a point, a line segment, a ray, intersecting lines or parallel lines from the following: A. The tip of a pen. B. A stretched string. C. Opposite sides of a scale. D. Beam of a torchlight. E. 2 adjacent edges of your book. Solution: A. Point. B. Line segment. C. Parallel lines. D. Rays. E. Intersecting lines. How many lines can be drawn passing through? In the adjacent figure, curves. The drawing which can be made without lifting the pencil from the paper are called curves. In mathematics, even a straight line is a curve, as it is drawn without lifting the pencil. Some of the examples of curves are given below. In the above figures, we find that There are two types of curves, open curve, closed curve. Let's study about these curves in detail. Open curve. A curve that is not closed or has an endpoint is called an open curve. An open curve does not end at its starting point. The following figures represent open curves. Closed curve. A curve which has no endpoint and completely encloses an area is called a closed curve. In other words, a closed curve has no breaks. It is continuous. It begins and ends at the same point. Each of the figures given below is a closed curve. Simple and non-simple closed curves. A simple closed curve is a curve which does not cross or intersect itself. A non-simple curve always crosses itself. Interior and exterior of a curve. A closed curve has a boundary. Due to this boundary, the curve has the following three parts: the inside or the interior of the curve, the boundary of the curve, the outside or the exterior of the curve. The adjoining figure shows the three parts of the curve. The shaded portion is the interior of the curve. The points A, B, and C lie in the interior of the curve. The points D, E, and F lie on the boundary of the curve. The points H, G, and I lie in the exterior of the curve. The interior of the curve together with its boundary is called the region of the closed curve. Polygons. A simple closed curve made up entirely of line segments is called a polygon. A polygon has 3 or more sides. The polygon having the least number of sides is the triangle. Given below are some examples of polygons: triangle, square, rectangle, pentagon, hexagon. The following table describes different types of polygons with the number of their sides. Name of the polygon, number of sides: triangle 3, quadrilateral 4, pentagon 5, hexagon 6, heptagon 7, octagon 8. Terms related to a polygon. Sides. The line segments which form a polygon are called its sides. In the given figure, AB, BC, CD, and DA are the sides of the polygon ABCD. Vertex. The meeting point of the two sides of a polygon is called its vertex. The plural of vertex is vertices. In the given figure, A, B, C, and D are the vertices of polygon ABCD. Adjacent sides. Any two sides of a polygon having a common endpoint are called adjacent sides. In the given figure, AB, BC, BC, CD, CD, DA, and DA, AB are 4 pairs of adjacent sides of polygon ABCD. Adjacent vertices. The endpoints of the same side of a polygon are called adjacent vertices. In the given figure, AB, BC, CD, and DA are the pairs of adjacent vertices in polygon ABCD. Diagonals. The line segments joining two non-adjacent or opposite vertices of a polygon are called the diagonals of the polygon. In the figure, AC, EC, EB, BD, and DA are the diagonals of polygon ABCD. Which of the following are polygons and which are non-polygon? Fill in the blanks. Angles. An angle is defined as a figure formed by two rays having the common starting point. The common starting point is known as the vertex of the angle, and the rays forming the angle are called its arms or sides. An angle is shown in the adjoining figure. In angle BOA, shown alongside, O is the vertex and OA and OB are the arms of the angle. The divider in our geometry box is a fine example of an angle. Let us keep one of its arms fixed and rotate the second arm. In rotation, we find different positions. These positions show different angles. Look at some angles shown below. Naming an angle. An angle may be named in any of the following ways. With 3 capital letters such that the vertex letter is written in between the other two. In the given figure, the angle can be named as angle POQ or angle QOP. Is a symbol used to represent an angle. With a vertex letter, if there is one angle having this vertex, in the figure, the angle is denoted as angle R. With a small letter or a number placed between the sides of the angle and near the vertex, in the given figure, the angles are denoted as angle A and angle 1 respectively. Remember, an angle can be named in 3 different ways. In the given figure, the angle can be written as angle ABC or angle B or angle 1. Triangles. Triangle is a polygon with 3 sides, or triangle is a closed figure formed by joining 3 non-collinear points. We use the symbol for denoting a triangle. The adjoining triangle can be named as triangle ABC, which is pronounced as triangle ABC. Other ways to write triangle ABC are triangle ACB, triangle BAC, triangle CAB, triangle BCA, and triangle CBA. Vertices, sides, and angles of a triangle. Sides. A triangle has 3 sides. In triangle ABC, its 3 sides are AB, BC, and CA respectively. Vertex. The point where any 2 of the 3 sides of a triangle meet is called the vertex of the triangle. A triangle has 3 vertices. In triangle ABC, the 3 vertices are A, B, and C. Angle. A triangle has 3 angles. When the 2 sides of a triangle meet, they form an angle at that point. In triangle ABC, 3 angles are angle ABC, angle ACB, and angle BAC. Elements of a triangle. A triangle has 6 elements, 3 sides, and 3 angles. Interior and exterior of a triangle. Interior of a triangle. The region enclosed by the 3 sides of a triangle is its interior. In the triangle given, the shaded part is the interior of triangle ABC, in which points P, Q, and R lie. Exterior of a triangle. The region that surrounds the triangle is its exterior. In the adjacent figure, points S, U, and V lie in the exterior of triangle ABC. Boundary and triangular region. When you refer to triangle ABC, you are actually referring to its boundary formed by its 3 sides, not its interior. In the adjacent figure, points X, Y, Z lie on the boundary of triangle ABC. Or you can say that they lie on triangle ABC. The interior region of triangle along with its boundary is known as the triangular region. Quadrilaterals. Quadri means 4 and lateral means side. A quadrilateral is a polygon having 4 sides. Top of a table, room floor, top of the roof, paper sheet, etc. are few examples of quadrilaterals, as all these examples have 4 sides. The adjoining figure is a quadrilateral named as quadrilateral PQRS. In quadrilateral PQRS, we have the following paths: 4 vertices P, Q, R, and S, 4 sides PQ, QR, RS, and PS, 4 angles, angle SPQ, angle PQR, angle QRS, an angle RSP. Diagonals, the line segment joining the opposite vertices of a quadrilateral, are called diagonals. A quadrilateral has two diagonals. In the adjoining figure, quadrilateral PQRS has PR and QS as diagonals. Opposite vertices. In the given figure, the vertices P and R, Q and S are the opposite vertices. Opposite sides. The sides PQ, SR and PS, QR are opposite to each other as they do not have a common endpoint. Adjacent sides PS, SR, SR, RQ, QR, QP and QP, PS are adjacent sides of quadrilateral PQRS as there is a common endpoint between two sides. Example, PS and SR have common endpoint S. Opposite angles, angle P and angle R, angle Q and angle S are opposite angles. Adjacent angles, two angles of a quadrilateral having a common side are called its adjacent angles. In figure, angle P and angle S have common side PS, angle S and angle R have common side SR, angle R and angle Q have common side QR, angle Q and angle P have common side PQ. Circle. A circular or round shape is the most common geometrical figure that we observe often in our everyday life. For example, a coin, a bangle, a wheel, the dial of a clock, a pizza, full moon and sun all resemble a circle. A circle is a simple closed curve, all points on which are at the same distance from a fixed point inside it. Parts of a circle. Center. The fixed point from which all the points on the circle are equidistant is called its center. In the adjoining figure, O is the center of the circle. Radius. The distance from the center of the circle to any point on the circle is called the radius. It is denoted by R. In the adjoining circle, OA, OB, OC and OD are radii, plural of radius, of the circle. Observe that OA equal to OB equal to OC equal to OD. That is, all the radii of a circle are equal. Remember, a circle is not a polygon as it is not made up of line segments. Diameter. The diameter of a circle is the line segment having its end points on the circle and passing through its center. Diameter is denoted by D. In the adjoining figure, Mn is the diameter of the circle. Any number of diameter can be drawn for a given circle. Relation between radius and diameter of a circle. As we can see in the figure that MO and ON are the radius of the circle and Mn is the diameter. Mn equal to MO plus ON. Mn equal to MO plus MO. As MO equal to ON, Mn equal to 2MO. Thus, diameter is twice the radius of the circle. Chord. A line segment having its endpoints on the circle is called a chord of the circle. In the given figure, line segment PQ is the chord. Remember, diameter is a chord, but a chord may not be the diameter. Diameter is the largest chord of the circle. Semicircle. A diameter divides the circle into two equal parts. Each part represents a semicircle. Arc. In the adjoining figure, portions arc ACB and arc BPA are two arcs. An arc is represented by the sign. If the arc of a circle is greater than a semicircle, it is called major arc. If the arc of a circle is lesser than a semicircle, it is called minor arc. In the adjoining figure, BPA is the major arc and ACB is minor arc. Sector. A region in the interior of a circle formed by an arc and the two radii joining the endpoints of the arc is called a sector of the circle. A pizza slice represents a sector of the circular pizza. The sector formed by a major arc is known as major sector, and the one formed by the minor arc is known as minor sector. Segment. A chord of a circle divides the circular region into two parts, called segments of the circle. The segment containing the center of the circle is known as major segment, and the one not containing the center is known as minor segment. Circumference of a circle. The perimeter of a circle is known as its circumference. In other words, the length of the boundary of a circle is called its circumference. Secant of a circle. A line intersecting a circle at two distinct points is called the secant of the circle. Concentric circles. Two or more circles having the same center are called concentric circles. In the adjoining figures, all the three circles have a common center, O. Multiple choice questions, MCQs. Chapter 10. Understanding Elementary Shapes. Line segment. We know that the line segment is a part of a line and it has a fixed length. In the given figure, AB is a line segment of line L. Comparison of line segments. Let us learn to compare two line segments by their length. Comparison by observation. In many cases, only by observing we can tell which line segment is longer and which is smaller. For example, look at one of the edges of your table and that of the book kept in your bag. Which one is greater? Obviously, the edge of the table is greater than that of the book. Look at the line segments shown below. It is obvious that line segment PQ is smaller than line segment AB, but it is difficult to find which line segment is smaller between line segment MN and line segment RS, as the difference is not clearly visible. Therefore, we need better methods of comparison. Comparison by tracing. To compare the length of two line segments, say AB and RS, by tracing. We first trace the line segment RS on a tracing paper. Then we place tracing paper over line segment AB such that A and R coincides and line segment RS falls along line segment AB. Now there can be three possibilities which can arise. If point S is ahead of point B, it means line segment RS is longer than line segment AB, or line segment AB is less than line segment RS. If point S coincides with point B, it means both the line segments are equal. That is, line segment AB equal to line segment RS. If point S lies before point B or between points A and B, it means line segment RS is less than line segment AB. That is, line segment AB is greater than line segment RS. Comparison using divider. Let us compare the line segments AB and CD by using divider. First, we need to measure the length of line segment AB using the divider. To do so, keep one end of the divider at point A and open it so that its other end touches point B. The opening of the divider is equal to the length of line segment AB. Now place one end of the open divider at point C of line segment CD. Depending on whether the other end of the divider touches point D of line segment CD or not, we will get the following results. If the other end of the divider touches point D, then line segment AB is equal to line segment CD. If the other end touches any point lying between C and D, then line segment AB is less than line segment CD. If the other end goes beyond point D, then line segment AB is greater than line segment CD. Measurement of line segments. Measurement of line segment by using a ruler. Let us measure the length of the line segment CD with a scale or ruler. For measuring the length of line segment CD, place the 0 mark of the ruler at point C. Put the edge having centimeter marks. Read the mark against the point D. Point D is at 4 centimeter. Thus, the length of line segment CD is 4 centimeter. Measurement of line segments by using a divider. To measure a line segment, say AB, by using a divider, open the arms of the divider so that the end tip of one of its arms is at A and the tip of other arm is at B. Now, without disturbing the divider arms, place the tip of one arm of divider on 0 mark of the ruler and read the mark against the tip of the second arm of the divider. Here, the other end touches the ruler at 5 centimeter, so the length of line segment AB is 5 centimeter. In the given figure, compare the line segment with the help of compass or divider and fill in the blanks using symbol greater than, less than, or equal to. Magnitude of an angle. The magnitude of an angle is the amount of rotation through which one of the arms must be rotated about the vertex to bring it to the position of the other. Angle as rotation of a ray. Suppose a ray after starting from its initial position, ray OA, rotates about the point O and takes a final position, ray OB. Then we say that an angle AOB has been described by the rotating ray with O as vertex and OA and OB as its arms. Comparing two angles. We can compare any two angles by the following methods. By observation. We can compare the two angles simply by looking at them. The more is the opening between two arms, the greater will be the magnitude of an angle and vice versa. In the given figures, angle PQR is greater than angle ABC because the opening between the arms of angle PQR is greater than the opening between the arms of angle ABC. By using tracing paper, let us compare two angles, angle DEF and angle ABC, by using tracing paper. We first trace the angle ABC on tracing paper and then place the traced angle ABC on angle DEF such that the point B coincides point E and ray BC overlaps ray EF. Now, there can be three possibilities. If ray AB lies beyond the ray BD, then angle ABC is greater than angle DEF. If ray AB lies between the arms of angle DEF, then angle ABC is less than angle DEF. If ray AB coincides with the ray DE, then angle ABC is equal to angle DEF. Different angles formed by rotation of the ray. Let us understand different angles by using a clock. Zero angle. When the clock shows the time 12 noon or 12 midnight, the angle formed between its two arms, that is rays, is zero angle. Complete angle. The needle of the clock shown alongside takes a complete turn along a circular path. After taking a complete round, it comes back to 12 again. The angle formed by this complete turn is called the complete angle. This angle is equal to 360 degree. Remember, an angle measures the amount of turn or rotation of one ray with respect to the other. The lengths of the fixed and moving rays do not affect the size of the angle formed by them. Remember, one complete turn along a circular path is called one revolution in a clock. The hour hand completes one revolution from 12 noon to 12 midnight, forming a complete angle. The angle formed by one revolution along a circular path is equal to 360 degrees. In fact, when you draw a circle, you make an angle of 360 degrees. Right angle. An angle that measures exactly 90 degrees is called a right angle. A right angle is formed when the clock shows time as 3 p.m. or 3 a.m. Remember, the standard unit for measuring an angle is degree, denoted by straight angle. As we know, while drawing a circle, we make a complete angle of 360 degrees.
If we draw half a circle, then the angle made would be 180 degrees, which is known as straight angle.
We can also define the straight angle as half revolution. Every 30 minutes, the minute hand of a clock turns by one straight angle. The angle between the hands of a clock at 6 a.m. or 6 p.m. is straight angle. Straight angle is of 180 degrees. Remember, an angle measures the amount of turn or rotation of one ray with respect to the other. The lengths of the fixed and moving rays do not affect the size of the angle formed by them. Remember, one complete turn along a circular path is called one revolution in a clock. The hour hand completes one revolution from 12 noon to 12 midnight, forming a complete angle. The angle formed by one revolution along a circular path is equal to kinds of angles. Acute angle, an angle whose measure is more than 0 degree but less than 90 degree is called an acute angle. In the given figure, angle AOB is an acute angle. Obtuse angle, an angle whose measure is more than 90 degree but less than 180 degree is called an obtuse angle. In the given figure, angle PQR is an obtuse angle. Reflex angle, an angle whose measure is more than 180 degree but less than 360 degree is called a reflex angle. In the given figure, angle LMN is a reflex angle. Example 1. What fraction of a revolution clockwise does the hour hand of a clock turn through when it goes from A. 3 to 6, B. 12 to 6? Solution. If the hour hand starts from 3 and stops at 6, then it covers 1/4 revolution or one right angle. B. If the hour hand starts from 12 and stops at 6, then it covers 1/2 revolution or 2 right angles. Classify the following as 0, acute, right, obtuse, straight, reflex, and complete angles. Observe the adjoining figure and state the kind of angles formed between the given directions. Measuring an angle. We have learned to classify the given angles as acute, obtuse, right, reflex, etc. Now we will learn to find their exact measure. This we can do by using a protractor. Measuring an angle using the protractor. Let us measure angle AOB given alongside using protractor. Place the protractor in such a way that the midpoint of its straight edge or zero edge coincides with the vertex O of angle AOB. Adjust the protractor so that ray OB is along the straight edge of the protractor. Out of inner and outer scales of the protractor, read the scale which has the 0 degree mark coinciding with the straight edge, that is, with ray OB. Here read the inner scale where OA touched ray. In this case, the reading is 50 degree. Thus, we write angle AOB equal to 50 degree. Remember, the sum of measures of the corresponding angles on the inner and outer scales of a protractor is 180 degree. Congruent angles. If the measures of two angles are equal, the angles are called congruent angles. In the given figure, angle AOB and angle PQR are congruent angles. Perpendiculars. Perpendicular lines. When two lines are at right angles to each other, or when the angle between two intersecting lines is 90 degree, they are said to be perpendicular lines. In the given figure, lines AB and CD are perpendicular to each other. When line AB is perpendicular to CD, we write it as AB perpendicular to CD. The following are some examples of perpendicular lines. The wall is perpendicular to the floor. Any two adjacent edges of the door or the window are perpendicular to each other. The adjacent sides of a sheet of paper or a postcard are also perpendicular to each other. English alphabet T and L are each made of two perpendicular strokes. Perpendicular bisector. A line segment that is perpendicular to another line segment and also divides it in two equal parts is called perpendicular bisector. In figure alongside, line segment RS bisects, that is divides into two equal parts, line segment PQ. At point O, it means line segment PO equal to line segment OQ. Note, bisect means to divide into two equal parts. Classification of triangles. Classification of triangles on the basis of sides. On the basis of sides, triangles can be classified in the following three types. Equilateral triangle. A triangle whose all three sides are equal is called an equilateral triangle. Here, triangle ABC is an equilateral triangle. Isosceles triangle. A triangle having two sides equal is called an isosceles triangle. Here, triangle PQR is an isosceles triangle. Scalene triangle. A triangle having no sides equal is called a scalene triangle. Here, triangle XYZ is a scalene triangle. Classification of triangles on the basis of angles. Acute angled triangle. If each angle of a triangle is acute, that is less than 90 degree, then the triangle is called an acute angled triangle. Here, triangle DEF is an acute angled triangle. Right angled triangle. A triangle in which one of the angles is a right angle, that is 90 degree, is called a right-angled triangle. Here, triangle AOB is a right-angled triangle. Obtuse angled triangle. A triangle in which one of the angles is obtuse, that is more than 90 degree, is called an obtuse angled triangle. Here, triangle PQR and triangle LMN are obtuse angled triangles. Relation between sides and angles of a triangle. Each angle of an equilateral triangle measures 60 degree. The angles opposite to equal sides of an isosceles triangle are equal. A scalene triangle has no two angles equal. Altitude of a triangle. A perpendicular drawn from a vertex of a triangle to the base is called the altitude of the triangle. In the given figure, PQR is a triangle and PS is perpendicular to QR. PS is called the altitude of triangle PQR. There can be one perpendicular drawn from each vertex of a triangle. Thus, there are three altitudes in a triangle. Median of a triangle. A line segment drawn from a vertex of a triangle to the midpoint of the base is called the median of the triangle. In the given figure, AD is a line segment which joins the vertex A to the midpoint of line segment BC. Thus, line segment AD is called the median of triangle ABC. There can be one median drawn from each vertex of a triangle. Thus, there are 3 medians in a triangle. Quadrilaterals. We know that a quadrilateral is a polygon having 4 sides. It can also be defined as a simple closed figure bounded by 4 line segments. Given figure shows quadrilateral ABCD. Trapezium, parallelogram, rhombus, rectangle, square, etc. are some special types of quadrilaterals. Let us learn about the properties of some special types of quadrilaterals. Properties of special types of quadrilaterals. Square. A quadrilateral in which all sides are equal and each angle is a right angle is called a square. In the given figure, ABCD is a square whose all sides are equal and all angles are right angles. That is, AB equal to BC equal to CD equal to DA. An angle A equal to angle B equal to angle C equal to angle D equal to 90 degree. Remember, a square is also called a regular quadrilateral as all of its sides and angles are equal. Rectangle. A quadrilateral in which opposite sides are equal and each angle is a right angle is called a rectangle. In the given rectangle PQRS, opposite sides PQ equal to SR and PS equal to QR, and all the angles are right angles. That is, PQ equal to SR, PS equal to QR, and angle P equal to angle Q equal to angle R equal to angle S equal to 90 degree. Parallelogram. A quadrilateral whose both pairs of opposite sides are parallel is called a parallelogram. Given quadrilateral ABCD is a parallelogram in which opposite sides are parallel. That is, AB is parallel to DC, AD is parallel to BC. Rhombus. A parallelogram in which all sides are equal is called a rhombus. In given parallelogram, all sides are of equal length. That is, AB equal to BC equal to CD equal to DA. So it is a rhombus. Trapezium. A quadrilateral whose one pair of opposite sides is parallel is called a trapezium. The figure given below shows trapezium ABCD in which sides AB and CD are parallel. If non-parallel sides of a trapezium are equal, then it is called an isosceles trapezium. In trapezium PQRS, the non-parallel sides PS and QR are equal. So it is an isosceles trapezium. Kite. A quadrilateral whose 2 pairs of adjacent sides are equal is called a kite. Figure shown on the right shows a kite ABCD in which AD equal to CD and AB equal to BC. 3-dimensional shapes. So far we have discussed various flat shapes. The flat shapes have 2 dimensions, that is length and breadth. In our everyday life we also see several objects like book, brick, matchbox, dice, etc. Each of these occupies space and has 3 dimensions, length, breadth and height. These objects are called 3-dimensional objects or 3D objects or solids. Cube, cuboid, cylinder, prism, cone, pyramid, etc. are examples of solids. Faces, edges and vertices. Flat surfaces of a solid are called its faces. Line segments where 2 faces of a solid object meet are called edges. A point where 3 or more faces of a solid meet is called a vertex. Let us learn about some solid shapes. Cube. It is a three-dimensional figure which has all the edges of same length. A cube has 8 vertices, 12 edges and 6 faces. Example, a Rubik cube, die, etc. Cuboid. A cuboid has 6 rectangular faces, 12 edges and 8 vertices. Example, a matchbox, a book, a chocolate box, etc. Cylinder. A cylinder looks like a round pipe. A cylinder has 3 faces, 1 curved face and 2 flat faces, and 2 edges. Example, a new pencil, etc. Cone. A cone has 2 faces, 1 flat face and 1 curved face. It has 1 vertex and 1 curved edge. Example, an ice cream cone, joker's cap, etc. Sphere. A sphere looks like a football. A sphere has 1 curved face. Example, a football, marbles, etc. Prism. A prism is a solid that has 2 identical and parallel bases which are polygon. The rest of the faces are parallelograms. If a prism has a triangular base, it is called a triangular prism. If it has a rectangular base, it is called a rectangular prism. Pyramid. A pyramid is a solid shape which has a single base or face as a polygon. The other faces of the pyramid are triangles that share a common vertex. If the base of a pyramid is a triangle, it is called a triangular pyramid. If its base is a square, it is called square pyramid. Name the following polygons. Nets of solids. A net is a 2-dimensional representation of a 3-dimensional object. The nets of various polyhedra can be made using paper, cardboard, etc. These nets are helpful in calculating and deriving the formulae for surface, area, and volume. We also get a clear idea of vertices, faces, and edges of various 3D objects. Net of a cube. It is made of 6 squares joined edge to edge as shown in adjacent figure. Net of a cuboid. Choose a suitable length, breadth, and height to get the net of a cuboid. Net of a cylinder. Cut 2 circles by choosing a suitable radius r. Cut a rectangle of length, h, and breadth equal to the circumference of circle of radius r. Join the 3 faces as shown alongside. Net of a cone. To make a net of a cone of radius r and slant height l, cut a sector of a circle where radius is equal to the slant height of the cone, that is L. The length of the arc should be equal to the circumference 2 pi r of the base of the cone. Also, cut a circle whose circumference should be equal to the circumference of the arc. Join the edge L to the other edge and the arc 2 pi r along the circumference of the circle to get a cone. Net of a pyramid, tetrahedron. To make a net of a regular tetrahedron or triangular pyramid, we need 4 equilateral triangles. Join them as shown in the figure to get the required tetrahedron. Net of a prism. Cut 2 equilateral triangles of same size and cut 3 rectangles of length of your choice and breadth equal to the side of an equilateral triangle. Join them as shown in the figure alongside to get the prism. Multiple choice questions, MCQs. Take the correct answer. Chapter 11. Practical Geometry. Construction of a line segment. We know that a line segment is a part of a line. It has two endpoints and its length is fixed. In the adjoining figure, AB is a line segment of line L. We can construct a line segment of given length in two ways, by using a ruler and by using both a ruler and a compass. Using ruler, suppose we have to draw a line segment of length 5 cm. To draw this line segment with a ruler, undertake the following steps. Place the ruler on a paper and hold it firmly. Mark with pencil 2 points, A and B on paper against the 0 mark and 5 cm mark of the ruler. Join the points A and B by moving the pencil along the ruler. AB is the required line segment of length 5 cm. Using ruler and compass. To construct a line segment of length 5.5 cm, using ruler and compass, undertake the following steps. Step 1. Draw a line M and mark a point X on it. Step 2. Place the metal tip of the compass on the 0 mark of the ruler and the pencil tip on the 5.5 cm mark as shown in figure. Step 3. Now place the metal tip of the compass on X and swing the compass to cut an arc on the line M at Y as shown in figure. Step 4. XY is the required line segment measuring 5.5 cm. Construction of a line segment equal to a given line segment. To construct a line segment equal to a given line segment AB, undertake the following steps. Step 1. Put the metal tip of the compass on A and the pencil tip on B. The opening of the compass is the length of line segment AB. Step 2. Draw a line L with a ruler and mark a point P on it. Step 3. Without changing the opening of the compass, put the metal tip of the compass on P. Step 4. Swing the compass to cut an arc at Q on the line L. Now, line segment PQ is the line segment equal to line segment AB. Construction of a circle. We know that the circle is a common geometrical shape. In our day-to-day life, we come across many situations where we find circles. For example, coins, CDs, bottle caps, bangles, wheels, chapatis, puris, pizzas, etc. are all circular in shape. Let us draw a circle of radius 4.5 cm with the help of a compass. Step 1. Fix a pointed pencil in the compass. Step 2. Open the compass for the required radius of 4.5 cm. To do so, place the pointed tip of the compass on the 0 mark of the ruler as shown in the adjoining figure. Now adjust the pencil end of the compass in such a way that the pencil tip touches the 4.5 cm mark. Step 3. Mark a point O on the paper. Step 4. Place the metal tip of the compass at O and turn it around so that it traces a circle. The figure so obtained is a circle of radius 4.5 cm with center O. Construct a line segment whose length is the difference of the lengths of two given line segments. Construction of perpendicular lines. Two lines or rays or segments intersecting each other at right angles are known as perpendicular lines or rays or line segments. Example, letter T, adjacent sides of a wall, etc. show perpendicular lines. To construct a line perpendicular to a given line through a point lying on it, drawing a perpendicular using ruler and set squares. Step 1. Given is a point P lying on a line L. Step 2. Place a ruler with one of its edges along L. Hold it firmly. Step 3. Place a set square with one of its edges along the already aligned edge of the ruler, such that the right-angled corner is in contact with the ruler. Step 4. Slide the set square along the edge of ruler until its right-angled corner coincides with P. Step 5. Hold the set square firmly in this position. Draw line segment PQ along the edge of the set square. Extend PQ with a dotted line. Line segment PQ is the required perpendicular to L. Drawing a perpendicular using ruler and compass. Step 1. Given is a point P lying on a line L. Step 2. With P as center and a convenient radius, construct an arc intersecting the line L at 2 points A and B. Step 3. With A and B as centers and a radius greater than AP, construct two arcs which cut each other at Q. Step 4. Join PQ. Line segment PQ is perpendicular to L. We write PQ perpendicular to L. To construct a perpendicular to a line through a point not lying on it. Drawing a perpendicular using ruler and set square. Step 1. Let L be the given line and P be a point outside L. Step 2. Place a set square on L such that one arm of its right angle aligns along L. Step 3. Place a ruler along the edge opposite to the right angle of the set square. Step 4. Holding the ruler fixed, slide the set square along the ruler till the right angle vertex of the set square touches the other arm of the set square. Step 5. Join PM along the edge through P, meeting L at M. Now line segment PM is perpendicular to L. Drawing a perpendicular using ruler and compass. Step 1. Given R a line L and a point P not lying on it. Step 2. With P as center, draw an arc which intersects line L at 2 points A and B as shown in figure on the next page. Step 3. Using the same radius and with A and B as centers, construct two arcs that intersect at a point R on the other side. Step 4. Join PR. Thus, line segment PR is perpendicular to L. That is, line segment PR is perpendicular to L. Constructing a perpendicular bisector of a line segment. A perpendicular that divides a line into two equal parts is called the perpendicular bisector. Let us learn to draw a perpendicular bisector of a line. Construct a perpendicular bisector, line segment PQ of a line segment AB of length 6.5 cm. Steps of construction. Step 1. Draw a line segment AB of length 6.5 cm. Step 2. With point A as center and radius more than half the length of line segment AB, draw arcs above and below line segment AB using a compass. Step 3. With B as center and the same radius as that in step 2, draw arcs cutting the previous arcs at points P and Q respectively. Step 4. Join points P and Q. Line segment PQ that intersects line segment AB at M is the required perpendicular bisector of line segment AB. Constructing an angle of a given measure using a protractor. Let us construct an angle of 70 degree. Steps of construction. Step 1. Draw a ray AB. Step 2. Place the center of the protractor at point A in such a way that its straight edge or zero edge coincides with ray AB as shown in figure. Step 3. To make an angle of 70 degree at point A, we will have to use the inner scale to the right of point A. Therefore, mark point C at the 70 degree mark of the protractor. Step 4. Take the protractor off and join AC by using a scale. Angle BAC is the required angle of 70 degree. Constructing an angle equal to a given angle.
Let us learn to construct an angle equal to a given angle.
Let angle AOB is the given angle. Steps of construction. Step 1. Draw a ray PQ. Step 2. Placing the compass at point O of given angle AOB. Draw an arc cutting rays OA and OB at C and D respectively. Step 3. Now with P as center and the same opening of the compass as in step 2, draw an arc cutting ray PQ at X. Step 4. With X as center and radius as CD, draw an arc cutting the previous arc at Y. Step 5. Join points P and Y and extend the resulting line segment to any point, say R. Angle QPR is the required angle having the same measure as angle AOB. Multiple choice questions, MCQs. Chapter 12. Symmetry. Line of symmetry. Look at the picture shown below. Remember, the line of symmetry divides the figure into two identical halves. Have you observed that the dotted line in each of the above pictures divides it into two identical parts or halves? If you fold the sheet of paper along this line, the two parts of each figure would cover each other completely. These figures are known as symmetrical figures, and the line that divides the figure into two identical halves or parts is known as line of symmetry or axis of symmetry. In a symmetrical figure, each half is a reflection or mirror image of the other half. If we place a mirror on the paper fold representing the line of symmetry, then the mirror image of one side of the figure appears exactly the same as the other side of the figure. Some shapes have one line of symmetry, some have more than one line of symmetry, while some shapes have no line of symmetry. Letters and figures having multiple lines of symmetry. Some letters of English alphabet have more than two lines of symmetry. Given below are some letters and shapes having more than two lines of symmetry. Square. As shown in the figure given below, a square has four lines of symmetry. Besides the lines joining the midpoints of its sides, a square is also symmetric about its diagonals. Check this out by paper folding. Equilateral triangle. An equilateral triangle has three lines of symmetry as shown in figure. Regular pentagon. A regular pentagon has 5 lines of symmetry as shown in figure. Regular hexagon. A regular hexagon has 6 lines of symmetry as shown in figure. In the following shapes, find the number of lines of symmetry in each case. Drag all the letters of English alphabet which have reflection and symmetry. We see reflection of objects in the mirror. The object and its mirror image are symmetrical with reference to the mirror line. The mirror line is similar to the paper fold that acts as the line of symmetry for two symmetric halves of a figure. We can say that The image is the reflection of the object across the mirror line. Observe the following figures that show the reflections of some English letters across the mirror line. Multiple choice questions, MCQs. Chapter 13. Perimeter and Area. Perimeter. The length of the boundary of a closed figure is known as its perimeter. The perimeter of a plane figure is the sum of measurements of all its sides. Unit of perimeter is same as that of length. It can be measured in meter, centimeter, millimeter, etc. Perimeter of irregular shapes. Let us try to find the perimeter of the following shapes. Perimeter of figure ABCDE equal to AB plus BC plus CD plus DE plus EA equal to 8 plus 6 plus 2 plus 10 plus 8 centimeter equal to 34 centimeter. Perimeter of figure PQRSTU equal to PQ plus QR plus RS plus ST plus TU plus UP equal to 3 plus 2 plus 2 plus 6 plus 4 plus 3 centimeter equal to 20 centimeter. Perimeter of figure EFGHIJ equal to EF plus FG plus GH plus HI plus IJ plus JE equal to 2.5 plus 9 plus 3 plus 4.5 plus 6 plus 5 centimeter equal to 30 centimeter. Perimeter of a rectangle. The given figure is a rectangle with length 12 centimeter and breadth 5 centimeter. We know that in a rectangle, opposite sides are equal. So, AB equal to CD equal to 12 centimeter and BC equal to AD equal to 5 centimeter. So, perimeter of rectangle ABCD equal to AB plus BC plus CD plus DA equal to 12 plus 5 plus 12 plus 5 centimeter equal to 34 centimeter. Thus, perimeter of a rectangle is the sum of all its four sides. Now, let length equal to L centimeter and breadth equal to B centimeter. Perimeter equal to AB plus BC plus CD plus DA equal to L plus B plus L plus B equal to 2 into L plus B. Therefore, perimeter of a rectangle equal to 2 into length plus breadth, or P equal to 2 into L plus B. Let us find the perimeter of the rectangle PQRS using the above formula. We know that perimeter of a rectangle equal to 2 into L plus B. Therefore, perimeter of a rectangle PQRS equal to 2 into 36 plus 24 meter equal to 2 into 60 meter equal to 120 meter. Perimeter of regular shapes or polygons. We know that a curve having the same starting and ending point is called a closed curve. A simple closed curve made up entirely of line segments is called a regular polygon if all its sides are equal in length and all its angles are equal in measure. A square and an equilateral triangle are the examples of regular polygons. Perimeter of a square. A square is a regular four-sided polygon. Perimeter of the square ABCD equal to AB plus BC plus CD plus DA equal to L plus L plus L plus L equal to 4 into L. Therefore, perimeter of a square equal to 4 into side. Let us find the perimeter of square with side 3.5 centimeter. Perimeter of square equal to 4 into side equal to 4 into 3.5 centimeter equal to 14 centimeter. Perimeter of an equilateral triangle. Let triangle ABC be an equilateral triangle. Perimeter of equilateral triangle ABC equal to AB plus BC plus CA equal to A plus A plus A equal to 3 into A. Therefore, perimeter of an equilateral triangle equal to 3 into side. Let us find the perimeter of an equilateral triangle with side 5 centimeter. Perimeter equal to 3 into side equal to 3 into 5 centimeter equal to 15 centimeter. From above results, we conclude that perimeter of 5-sided regular polygon, pentagon, equal to 5 into side, 6-sided regular polygon, hexagon, equal to 6 into side, 8-sided regular polygon, octagon, equal to 8 into side, n-sided regular polygon, n-gon, equal to n into side. Find the perimeter of the following. Area. The magnitude of the measurement of the region enclosed by a closed plane figure is called its area, or the amount of surface enclosed by a closed figure is called its area. Applications of area. The concept of area is widely used in everyday life, as is evident in the following examples. The cost of a land to be purchased depends on its area. More the area, more is the cost. To calculate the amount of glass required for a window, you need to know the area of the window. To determine how much colored paper is needed to cover a bulletin board, you have to calculate the area of the bulletin board. A carpenter uses the measurement of area of proposed woodwork to assess the materials required for completing the work. Finding area by using graph paper. We can find approximate area of a region enclosed by any simple closed figure by using a sheet of squared paper and counting unit squares. Observe the following figures drawn on the square paper. We may also come across certain figures on graph paper that do not enclose all the unit squares completely. They may cover more than half portion, or less than half portion of same unit squares as shown in figure. To calculate the area of a figure that does not cover all the unit squares completely, we have to go by the following steps. Take the area of one full square as one square unit. In case of a centimeter square sheet, the area of one full square will be 1 square centimeter. Let the number of complete squares be m. Take the area of more than half covered square also as 1 square unit. Let their number be n. Take the area of an exactly half covered square as 1/2 square units. Let their number be p. Ignore the square which are less than half covered. So estimated area of the figure equal to m plus n plus 1/2p centimeter square. Area of a rectangle. Let's learn to find the area of a rectangle using a graph paper. Observe the following figure. Count the number of squares of area 1 centimeter square, each enclosed in the rectangle shown in figure. Clearly, it contains 3 into 6 such squares. Because the figure has 3 rows and each row has 6 squares. If we count the number of squares in columns, then the total number of squares would be 6 into 3, because there are 6 columns and each column has 3 squares. Therefore, total number of squares equal to 3 into 6 equal to 6 into 3. Area of rectangle equal to 6 into 3 square centimeter equal to 18 square centimeter. Thus we have area of a rectangle equal to length into breadth. Length of rectangle equal to area upon breadth. Breadth of rectangle equal to area upon length. Area of a square. Since a square is a special case of rectangle in which the length is equal to breadth, so area of a square equal to length into breadth equal to side into side square units. Let side of the square be A. Then area of square equal to A into A. Example 7. Find the area of a rectangular photo frame whose length and breadth are 16 cm and 10 cm respectively. Solution. Length L equal to 16 cm, breadth B equal to 10 cm. Area of photo frame equal to L into B equal to 16 cm into 10 cm equal to 160 square centimeter or 160 centimeter square. Remember, in calculating the area of a rectangle and square, we must make same units for the length and the breadth. Find the area of rectangles with following dimensions. Multiple choice questions, MCQs. Chapter 14. Data Handling. Pictograph. Till now we have learnt about the presentation of data through tables. There is another way of presenting data in the form of pictures. As compared to data tables, pictures help us to understand data more easily and effectively. Representation of numerical data using pictures or symbols is called pictograph. Example 3. Given below is the data related to the sale of computers in a shop in 6 months. Month, number of computers sold. January, 100. February, 150. March, 75. April, 50. May, 125. June, 200. Make a pictograph for the above data. Solution. Let one picture equal to 50 computers. Half picture equal to 25 computers. So the required pictograph is as shown below. Interpretation of pictograph. Once you know how to draw a pictograph, it becomes easy to interpret the same. Example 4. The pictograph given below shows the number of persons traveled from city P to city Q by bus on each day of a certain week. Scale. One picture represents 5 persons. From the pictograph, answer the following questions. On which day the bus was most crowded? How many persons traveled on that day? On which day the bus operator had the least earnings? What were the total earnings on that day? If the fare per person was 5 rupees. Solution. A. Tuesday, 45. B. Sunday, 50 rupees. The following data shows the sale of TV sets by a company during the last 6 months. Bar graph. A bar graph is a pictorial representation of data by a number of bars of uniform width. There are 2 types of graphs used to display data: horizontal or vertical. In vertical bar graphs, x-axis horizontal line is used for labeling. In horizontal bar graphs, y-axis vertical line is used for labeling. The vertical bar graph is the most effective means of comparing sets of items. However, the disadvantage of vertical bar graphs is that they lack space for text labeling at the foot of each bar. When category labels in the graph are too long, a horizontal bar graph is a better option for displaying the information. Remember, all bars should have the same pattern or shading. Interpretation of a bar graph. Keep in mind the following steps while constructing a bar graph. Draw two mutually perpendicular lines on a graph sheet. The horizontal line is called x-axis and the vertical line is called y-axis. Both lines intersect each other at point O. Along x-axis, mark the standard things or categories whose variation you want to show on the bar graph. Use a suitable scale on y-axis in terms of amount, number, percentage, etc. to record the variation along y-axis of the things or quantities represented along x-axis. Draw bars of equal width on x-axis, keeping uniform gaps between them. Multiple choice questions, MCQs. Tick the correct answer. Tick the correct answer.